Hello, everybody, and welcome. Am I live? Did I make it? I did make it. I am live. Gonna close that now. Hello, everybody. How is it going? Let's make our announcement. Let's go here and at notice so I don't forget. Do our little red circle. Live. Type. And this is going to be compiler, bruh. Why not? Typing is hard. Where are we live? We are live at twitch.tv/Linzer. Beautiful stuff. We are live. Back to the compiler, baby. That's right. We're doing it all. I gotta change the title of the stream. I forgot. I straight up forgot. Okay. Not scene transitions, you dummy. Oh, I've done bad things. Okay, hold on. Compiler development. Woo. It's going to be Linzer went live, sure. Yay. Okay, we changed the title. Sorry about that. The notification's probably wrong, which I find hilarious. Terrific Table 55 says hi. What's up, Terrific Table? You were in here yesterday. It's so good to see you again. Streamer 2022. It's been a while. It's been like a month since I've worked on the fun compiler. So let's just try and build it. Okay, so it looks like we have build, we have CMake. So I'm just gonna open up CMake at the bottom here. Getting better with my new keyboard. How are you doing, Terrific Table? What is up with you today? I am just gonna work on the compiler a little bit and see how it goes. So we're just gonna build, and build func. And then let's just do an example that we know will fail. We're in the middle of stuff. Oh. Let me just close Emacs. Perfect. Look at that. Look at us. Okay, what do we got? Okay, so it looks like we were able to build it and link it into an executable, which we then ran with a command line parameter of our greatest common denominator example. So let's open that. Oh, hold on. Let me load the editor mode. Okay, now I can open examples, greatest common denominator. Then I can switch into mode. And now we have syntax highlighting. Look at us. How fancy. And this code on the left is the same as this code on the right. It's just slightly more confusing. Terrific Table says, I'm trying to find out if I killed my CO2 sensor or not. I would probably do that outside in a well-ventilated area. Lamau. Anyway, the stuff on the left is our source code that our compiler is compiling. It is a language I made up, and it's scuffed right now, but it's working. Terrific Table 55 says it's a small SCD30. I don't know what that is. I'm sorry. Terrific Table says, but it's time outing since like an hour ago. RIP. Mr. Mugame says, fart into it. Oh god. Twitch chat never change. That may work. That may work. Terrific Table says, I'm gonna try it. Oh, what have we done? What have we done? Okay. This code on the left is the same as on the right, it's just in a different form. This is in the intermediate representation of the compiler. So you can see that F1 and F2 are functions, which refer to the main function, and this function that's defined right here technically here. This lambda function, you can see that it starts with 2 parameter references in its first basic block. So there are 2 parameters, that's correct. Then we have a load 8 and load 9. This is in preparation of this a equals b, if a is equal to b, right? If a is equal to b, well, we need to load a and load b, and these 8 and 9 refer to these values that are basically returned from these instructions, or the result of these instructions. So the result of these instructions, 8 and 9, are parameter references. So we load 8 and load 9, we load a and b, both of our parameters. Then in 12, we say equal 10 and 11. So when we loaded them, we then say, okay, equal 10 and 11, which effectively just means, are these equal? And if so, set the result of 12. And then on 13, we see a branch conditional on 12 to bb3 or bb4, which is our then and otherwise. So 12 is our conditional if 10 and 11 are equal. And then we say conditionally, if 12 is non-zero, jump to this block here, bb3, basic block 3, which just loads a once more, and then branches to bb8, which is the exit, down there. We'll get there. Otherwise, if it is 0, if a does not equal b, right, if it's failing, then we jump to bb4, basic block 4, loads both a and b once more, does a different comparison, a less than comparison, and then branches on that conditional to 5 and 6. So basic block 5 is here. You can see that we load GCD Euclid, the address that we're going to jump to, which we can probably do later, but it's fine right now. We load 8, 9, and 8 because we need a, and then 9 and 8 are for this subtract that are about to happen, 22 and 23. So then 24 is our second parameter, as you can see. 21 is our first parameter, so we have a and b minus a. And then we call 20, which is our actual function address. And then we branch to bb7, which has a phi node, which basically says the result of this node is either going to be 32 if we branched from bb6, or 25 if we branched from bb6. That's not right. Pretty sure these should be different. No, I think that's right. If Sir Aid was here, he could tell me, but I'm pretty sure that's right. Because it records the latest in the control flow of reaching it. But 25 should be from here, and then we go to bb7. So it seems like this should be bb5 here. But who knows? Maybe it's correct. I don't think it's correct. In any case, we then branch to bb8 just like we did from up here. And bb8 is effectively the return. So we just have either branching from, again, these are wrong, 34 here, or from 14 up here. And that will be our return value here, as you can see. That is the basics of our IR for our greatest common denominator. I know it's a lot. And then we're saying assertion failed, emit code based on IR in context. So this is having to do with our code gen being halfway done, because that's where I stopped. So if we look at actual codegen.c, which is what gets called on the AST after it's been type checked, you can see that basically codegen creates a context. It opens a code file and everything, don't worry about that. It creates a context, and then we just call this codegen program, and then we call IR set IDs, IRF emit, and this is what's printing out all of this lovely output, IRF emit to standard out. And then we say codegen emit context, and codegen emit pulls us into our actual backend, right? So that'll bring us to x86-64. I mean, it's a wrapper right here, you can see it. just so you know. It was on screen, I didn't mention that. My Twitch chat may just be frozen. I'm gonna double check that there's been no messages. There may be a sound, because I'm opening Twitch front page. Was I fast enough? I was fast enough. We good. Yeah, okay. My Twitch chat in OBS just froze. Yeah, Mr. Mugume, I don't see your newest chats. Hold on. I think I can reconnect. Refresh. Okay, I see him now. We're good. I did it. Sorry about that. Okay. Anyway, this is our x86-64 backend. And the idea is that we have some stuff to do. So when we call CodeGen emit, the first thing we do is emit into the code. Okay, this string, right? Which technically, I don't think we even need a format string here, but it's fine. We say, okay, we're in the data section right now. So this is modifiable data. And then we define all of our global variables and external functions and stuff like that. Oh no, we skip external functions. That's what that is. And then we just allocate space under the proper symbol, and everything goes well. How about that? So that's currently all we're doing. So if we take a look at the code that was output here, you can see that all we have here is actually, greatest common denominator, is actually the global variable declarations of GCD Euclid. Because this is the only global variable. And that's all we're currently codegenning. Because when we call, we don't ever call anything. We just say to do it. Pretty bad, right? We have all this stuff from before where we would create, we would call these functions directly from CodeGen instead of creating an IR. But now we create an IR and we want to call these functions based on the IR. So now we have to do that translation. But the thing is, a lot of these need registers. And we don't know what register to pass. Before we were doing some very basic register allocation, as you can see, where we would allocate and deallocate everywhere, all over the place. But it turns out you're able to allocate all at once at the beginning. So today we're going to start on register allocation. Mr. Mugume says, does a func declaration not need any keyword? You are correct. A function is just another type in the language. It's just the same as any other variable. But yeah, so we have first-class functions. They are first-class citizens in this language, which means you can pass them around, for example, as arguments into functions. We've solved the downwards funarg problem. Upwards we're still working on, but it's definitely doable with closures instead of lambdas. That's the one. That's fine. Okay. Register allocation. Are you ready to get into graph theory again? Do I still have it? Docs. What do we have? Developers.pdf. We're checking it out. Oh man. If you don't know, there are tech files available, LaTeX files available, which you can compile into PDFs and read all about this compiler and how it works, hopefully. Yeah, we definitely have to fix all this. This isn't that helpful. This was me learning. Oh, this is pretty helpful. Oh, nice. And then this is what Sarade wrote. Yeah, this is very nice. Okay. So, is this what Sarade wrote? Feel like it is. Okay. Effectively, register allocation. The phi IR instruction represents a merging of multiple temporaries into a new temporary. The temporaries to be merged are referred to as phi's arguments. A web is a list of temporaries that must be stored in the same hardware register. Okay, I don't think we even use webs anymore. I don't think we need to build webs. So let's ignore webs. Must have also been me, because this is very abrupt and makes no sense. Serade would never allow for this. But I would. So basically, what we're gonna have to do is figure out which registers won't, like which of these, here, let's look at the compilation output. Which of these values can be stored in the same register or can't be stored in the same register. Either way, it's the same problem, right? Just inverse. So for example, 37 is just the return, but the return value is 36. So 37 won't actually return anything. It doesn't need a register, so we can just ignore that entirely. Whereas phi does need a register. And with phi here, we can go, hey, wait, 34, that's in basic block 7. That's also a phi, let's not do that one. 14, that's in basic block 3. That's a load of 8. That sounds like a load of crap. That's a load of 8. Right? So we do a local load of the 8, which is a parameter reference, which means this is just the parameter's value at this time in the program. So this parameter value, we can actually store in the same register as this phi instruction, because 14 is actually only ever used in this phi instruction. So nowhere in here is it ever used, which means that we can just replace this phi instruction, the register that it's placed in, with whatever 14 is, because 34 is guaranteed to be able to also be placed in it. There's no way we'll be able to reach this and then still need this data because we branch right to BB8 right after. Does that make sense? This is complicated, but it's gonna hopefully it makes sense. Hey, look, I closed Emacs. I'm good at that. Okay, don't do that. What are the buttons? What are the rules? Okay, hold on. Okay. Sorry. I don't think there's going to be much in this header, because truthfully, oh man, what has happened? My computer is not liking me today. That's for sure. Serade says, yep, what's up, Serade? How good, how good? What going, what going? I wish ClangD was just, like, better. I have to close it from the task manager all the time, because it just keeps opening new ones. Okay. How's it going, Serade? You may be familiar with this little ditty that we're about to do. We are about to do it. Okay. So, okay. Serade says, I'm currently doing my stats assignments, so we're somewhat decently. Lamau. Why ClangD? Just closing the 8 or so ClangDs that open while I'm talking. Okay. So it says ClangD is causing problems. Tell me about it. Yeah, it just I don't know why. It just keeps opening more ClangD. There's like, it's just every file I open starts a new ClangD process, and it's a little scary. And it starts like 8 of them. Just keeps starting. You know, classic ClangD stuff. It might be Emacs though. I wouldn't put it past it. Sorry, it says tell me about it. Yeah, ClangD ate like 60 gigs on your format, right? Sure, sure. 100 gigs is a perfectly reasonable amount of memory for an LSP. Lamau. Okay, so we're gonna need like some place to store all the stuff. That's really descriptive, I know. There was a commenter that mentioned that this name doesn't need to be here, the struct tag. What did I just do? This name doesn't need to be here, the struct tag. You can just use an anonymous struct, and that's true. Just wanted to mention it. So it says 60 gigs of RAM, 40 gigs of swap space on top of that. Yikes. Sorry, it says it doesn't. Yeah, the name does not need to be there, but it's fine. I don't care. So I'm pretty sure we're going to need like the codegen context, which is a thing in codegen.h, right? And this is going to be like our main context because we're going to need to know, we're probably going to need the context for variable lookups if we ever need to do stuff like that. Or maybe global variables, or I don't know. Do we ever need the context? I'm sure we do. So it says that doesn't work if you need to store a pointer to the struct in the struct. That's right, you need the struct tag. But otherwise you can omit the name. You know, this seems backwards. Shouldn't this be in the codegen context? Maybe. Maybe. Not every platform will need registers though. So sometimes we'll codegen without register allocation. So I'm just trying to think of what we're going to need to store. I know we're going to need to store a lot of amounts of things. So we're going to need to store like the amount of register. Oh, crap. The register count, right? And then we're also going to need like how many argument registers are there. So we're going to need an argument register count. Phone just went off. One sec. Okay, we're good. We're still good. Yeah, the register keyword strikes again, says Saray. It will always strike again. I've lost count of the number of times I've tried to name something register. I do it every time, to be honest. We're probably also going to want like a register type so that we can specify what a register is. This is probably going to have to be in codegen forward so everybody knows about it. See, here we have typedef int register descriptor. Oh, we already have typedef struct. I think these we can yeet. I don't think we need these anymore, right? For after register allocation. Register is actually just going to be an integer. An index into an enum or an array. When are you going to write that testing framework in algol 68, Lamauserate? Listen, do you ever just say something and then wish you didn't? That's fine. Sorry, it says we could use that for the OS too. Oh god, no. If anything, use the one I wrote in Pascal. It's so much better. Pascal is actually a nice language. Algol 68 was something I thought would be fun, and then I start to read the spec and I'm like, I don't have high enough IQ for this. What is it? So it says, no, I totally have no idea what you mean. Algol is a nice language. What do you mean? Don't read the spec. No one gets it. What do I read then? There's all I could find is that dang PDF. So we're gonna have to store like what the result register is, like where function results. I should probably comment on some of this. Where function results ends up. And where is kind of facetious. In which register the every function result ends up. That will change eventually, I'm sure, because that sounds way too limiting. And then, oh, here's the thing. Okay, hold on. Okay, so we're gonna have to basically we have the count, which means that we can basically just do our own little dynamic array, right? I think that's fine. What did I type there? I don't even know. What it? Huh. Nope. It's right the first time. And then this is going to be argument registers. Yes, yes. This is starting to make sense. Okay. Sraid says, read the manual for Algol 68 Genie. Oh god, anything basically that isn't the spec. The Algol 68 spec makes the C++ standard look like a children's book. I personally think Algol is really nice because you can have spaces and variable names. That is very cool. Forget snake case and all that. Space case is definitely my favorite naming convention now, lol. How does that work? Like, how does what? Spaces and variable names just break my parser brain. I'm like, how would you even parse that? That sounds impossible. I love how backwards this sentence is. Why are you mad about including code gen? Okay. So then we're gonna have to have some way to like create one of these, I'm pretty sure. That would make sense to me. Sraid says it works because Algol doesn't care about white space and types have to be all caps. That's how and why it works. Oh, nice. I just dropped everything and ran home when you went live. What's up, Lander XT? How's it going? It's so good to see you. Thank you for tuning in. We're working on the compiler again. Can you believe it? Basically, types and keywords are all caps. Interesting. So they made types keywords effectively. And regular identifiers all lowercase. That's pretty cool. I didn't know that. That's going to help me a lot. Okay. Okay. So we're going to have like something that returns one of these, right? And this is going to be allocate register info. Registers info. Allocate register allocation info. Here's what we'll do. Whoops, not that. Here's what we'll do. Allocate info prefixed with register allocation. That's how it goes. Okay, so what are we going to need? We're going to need a code gen context. Okay, we're going to need a lot of things, so we're going to need a code gen context and make sure that it's not null. Whoop. Things are hard. Okay. We're going to need the context. We're going to need the register count. So we'll just do all general registers count. Is this all registers count? General registers? Do you know, Saraid? Having not programmed in C for a while now, this makes me really miss constructors. Well, yeah, you betcha. Is this general registers or all registers? I don't think we ever need rip in the register allocator. Right? These are going to be general registers. The general purpose registers are racks, RBX, etc. Exactly. All the ones that there's 13 of them, right? I'm pretty sure that's what we need here. So this is general purpose registers, and these are the argument registers out of the general registers. But we don't actually ever need to reference RIP or anything in the register allocator, hopefully. RIP, RSP, RBP aren't GPRs. Perfect. Okay. I think that's fine then. So this is the general register count. And we can say, okay, if general registers count is equal to 0. Then, oh boy, new keyboard, spicy things. Please don't allocate rip, lol. Yeah, we'll use the instruction pointer to store some data real quick. Lamau. We should probably like return an error, but this is fine for now. So are we just going to be passed an array of registers? How about we just do that? We just say this is a register array of register count. That way we can fill the enums out here, basically. So we can say not general registers, return null. This is going to be a lot of error checking. I think that's fine for now. Okay, we're going to need the same thing. Oh god, me hitting the wrong buttons again. We're going to need the same thing when it comes to... Okay, then we're going to need the result register as well. Okay. It's been a while. Don't at me. Okay. Argument register count equals, okay, argument registers count. That's a confusing one. Okay. And some implementations may have no argument registers, so we don't want to check for 0 there. But we do, I mean, that could also be null then. Oh, by the way, I've mentioned this like 10,000 times before, but vector.h is still in my branch. Should you ever be interested in using vectors in lieu of lists, just saying. Bless. I like linked lists. That's my issue. I'm attached to them. And we'll say result register equals, whoops. I'll get there, don't worry. There we go. Okay, this is probably going to be an arrow. I should make a button in QMK and just bind it to insert the arrow. That'd be nice. Turn it on for C code. See, I just find myself disliking linked lists more and more every time I have to use them. Crazy. I love them. They let me build things. You know my text editor? Linked lists. You know my OS? Linked lists. You know my compiler? Linked lists. So it says that totally doesn't have anything to do with some sort of horrible bug we had to fix recently in LenderOS. I'm sure it doesn't at all. Not even related. So good. Okay, so we're going to allocate some info. And this is going to be a register allocation info thing. Info equal to allocation of one size of. Okay, we're going to do it. We're going to do it. You have won me over. We're going to have to include standard lib, but again, this won't be defined here eventually. This is in the header, so we won't include standard lib yet. We'll wait until after we move it. Okay, so we'll say info context is equal to context. Sorry I'm so slow inserting these symbols. I have a new keyboard and it's definitely a new keyboard. I am still getting used to it. Emacs magic, thank you. Oh, okay. That was me. I just opened Feedback Hub. I don't even know how I did that. Did I hit the Windows key somehow? Nice. I don't. Oh. Just closed every window. Hold on. Gotta open everything back up. Now. Okay, yep, just open Feedback Hub once more. Hang in there. Okay. Mr. Mugame says, I have to implement queues with an array in Java. OFN go brrr. OFN is fine. Sraid says, just make every function inline. That way you only need headers. SQLite moment. Oh god. Sraid responds to in Java, my condolences. Lamau. So we set the result, the context, and then both the registers and register count. Everything is being set. That should be everything we need. Okay. And then we just are going to need like array. It's going to be, I don't know, a void, I guess. It just does it. Do the thing. Takes in a register allocation info pointer. You didn't see a thing called info. So if not info, return. Just a basic safeguard to make things a little easier to catch. Mr. Mugame, yeah, I'd rather write raw JVM bytecode, probably even less boilerplate. Okay, array is gonna have to do a lot, so maybe we should just move it already. So let's make register allocation dot c. Let's include codegen slash register allocation dot h. Include standard lib, because we use callic. I always feel like I'm saying cowlick. And then do the same thing here. Bop, bop, bop. Okay. There we go. Allocate info. You ready for the war to start? Saraid. Shh. No, you're right. So, Lens, I don't like the name ir.h. We need to spell it out. How's anyone supposed to know what that means? Also, Lens, RA. But the fact that it's in register allocation.h means people will know what it means. See, it's intuitive. It's not about it being abbreviated, it's about it being intuitive. Time to make a PR to rename the files to ir.h and ra.h. Lamau. Nah. Okay, so rah ooh la la. What's up about romance? What do we need to do? So, hold on, let me get out my notes. I wrote notes last night. Okay, register allocation, are you ready? Okay, first, we're gonna do phi to copy. Okay, what is phi to copy? So we're gonna have this thing, wish it's easier to like center something within equal signs. I know it's not like the difficultest thing, but it's not easy. I'm just gonna do something like that. Yeah, we'll do that. Okay. Sorry, what is phi2copy? A massive headache is what it is. It's not too bad. So we're just gonna have phi2copy called with info. That's it. Nothing too complicated. And now we're gonna iterate over the entire everything. Right? So we're going to iterate over every function. Remember from the IR, there's functions, basic blocks, and instructions. So we're going to basically iterate. I need comp mode, please. Complete me. Okay, that's much better. Let's make this a little bigger. Okay. IR function, info, and we would basically like to say context. And then within this, you can see that all functions is our first function. While function, we can probably do a for loop. Function equals function. Excuse me? No completion? No completion here. Next. Is that not right? What did I screw up? It's complaining about something. Incomplete definition of type struct IR function. Huh. Is that an intermediate representation? That's probably where it is, huh? There it is. Yo, intermediate. That one. That's the one. Thank you. Okay, we got it. So it says, you know, this is why you use macros for this. Why? There's literally built-in things into the language to do exactly this. I mean, this can go here. You know what I mean? We're going to need it later, so we can't, but it could. And then each one of these, we have a block within. Right? And the block is going to equal the function first block at the beginning. And then, while block exists, also there's a space here. Block is equal to block. Guess what? It's a linked list. Next. And then, finally, ooh, okay, I just took a screenshot. Don't worry about that. We can look at each instruction itself, which is going to equal block. Yep, that's good. That's what I wanted. Jesus. I am slowly getting worse with this keyboard. Okay. And then we can go to instructions. And then we can say, wow, instruction. Instruction equals instruction next. How about that? So it says, and include the right headers. That also helps. Lol. Sometimes. It can help from time to time. I guess we can put this in here. I don't think there's any reason we need it without. Okay. So for every instruction, if this instruction is of a certain type, what is it? IR type. Is it just IR underscore something? Yeah, it's probably just IR5. Okay, so if we have a phi node, Okay, here's the thing. So first of all, I'm pretty sure we can just say there's something we can get done right away, which is that if instruction, oh god, value phi. So let's, yeah. Okay, if this and not that. Okay. This says if we have a phi argument and we do not have two phi arguments, two or more. So this means that if we have a single phi argument, that means that you can basically just replace the phi argument with a copy, I think. So single phi argument, I wish I set up fancy keyboard stuff for this, I didn't. So we have a single phi argument. And this means that we can replace it with a simple copy. Right, because the phi can only ever be reached from one place, so we can just replace the phi with a copy, and everything's Gucci. How do we actually do this? Well, to do this, one, we're going to have to alter the instructions type, right? It's going to have to equal an IR copy. Is that not a thing yet? Okay, we don't have an IR copy. That's probably an issue. So let's check out ir.h. We do not have IR copy here, and that would be an issue. So just going to go ahead and add in IR copy. We're going to add it in next to phi and put those next to the branch. Oh no, we have so much more math to handle. We need and, or, bit shift left, right. We need multiply, divide. There's some extending to do. Okay, so IR type equals IR copy. But what value does this have? Right, because this is basically a tagged union. So a copy is just going to copy another instruction. So it's just going to reference something. Whoops. And what is it referencing? It's referencing the phi argument. So we're basically not really changing much, actually. I know, this isn't right. From the phi argument's argument, right? So the phi argument value is the actual IR instruction that the phi argument points to, not the linked list. Okay. And in doing so, we basically ensure, oh god, yeah. So this just replaces it with a copy, and then we can continue to further instructions. Does that make any sense? Is that insane? I think that makes sense. Okay. Trade says this is already broken. I love it. As long as it works. I'm pretty sure this would work. You forgot about blocks that have multiple successors. It's multiple successors. Like a branch conditional. Why do you say that stuff? Why do you say things so confusingly? So blocks with multiple successors. So basically a block that has a conditional branch. It can go to different basic blocks based on its branch. You just said, remember that problem. I don't. If there's a single phi argument, then that means you can just replace it with a copy. It's just a copy of the argument. It's nothing else. It's not going to be anything else. There's only one predecessor. We copy it into a new instruction, and then I wrote about that in the RA PDF I made. Well, we'll see how much it breaks things. And then I'll read about that when I can. Okay. Now, if we reach this point, where are we at? We can also just comment this out, because this should almost never happen. So now, if there's not just a single phi argument, then there's either no phi arguments or many phi arguments. Several, I should say. So we're just going to loop over all the phi arguments. So let's just actually get an iterator. One of these things. Phi arg. Yeah, I don't like it, but I'll keep it. Okay. And then that's gonna that's gonna equal this thing. Let's just name it phi. That'll make this a little easier. Perfect. A little more readable. Okay. This breaks because it would perform the copy irrespective of what block you branch to, even if you're only supposed to copy if it branches to true or else. Why would you only need to copy if it branches elsewhere? I'm confused. I'm leaving it. Listen, you're probably describing a corner case that is correct and that I probably am getting wrong here. But we're going to see how much it breaks things before we change it. We've got a long way to go. And if you tell me in the first 5 lines, like, nope, you gotta stop, that's wrong. I'm just gonna keep going. I'll fix it when I can. And then phi equals phi. Next argument. I don't know if we're gonna need to do this, but this is kind of just what I did out of habit. Okay. And for each of these arguments, okay. Classic. For each of the phi arguments, we basically insert a copy. Where we insert it depends on some complicated factors that have to do with control flow. I think that's a succinct description. So this is kind of driving me crazy. I don't know. What do I like? Is that fine? It's kind of fine. That separates the for loop from the everything else. I like it. Whoa, okay. Okay, it's not the best, but given what we have to deal with here, it's not too bad. We're doing it. Okay, so now also I recommend you put an assert to something somewhere that checks that there aren't 2 phis in one block, because if there are, we'll pray that there aren't, pretty much, because that case is horrible. We'll just have it break things when it breaks things. Then we'll see if we can fix it. And if we can't, we'll be like, okay, it's probably this because there's 2 phis in this basic block. It seems like an easy thing to catch and a hard thing to program. Not a good thing to do at the start. So for every phi argument, we're basically going to want to replace it, right? So we're going to create a copy, I think. What did I call it? IR instruction? So it looks like I have an instruction macro. Why did that not work? Okay, there we go. So name of the instruction, copy, given type. Oh, Jesus. Oh, I went into the wrong keyboard layer, rip. And then this is going to be IR copy. And I think that that actually expands to the whole declaration. Okay. Yep, classic. Okay. And Sir Aid, you're going to yell at me for this. We're just going to insert the copy before the argument. I think this is fine. You know, I think that's backwards. It's not backwards. That's probably better. Do we have insert instruction before? We probably don't, do we? We have IR insert. That may not be right. Intermediate representation. So IR insert says insert at the end. We don't have insert before or anything like that. Well, I guess we just go for it. So what do we do? To insert an instruction before. Didn't expect to have to write this. Okay, insert instruction before. We're going to need two instructions, A and B. Oh, it's probably after. Yeah, you're right. Sorry, it says, yes, let's insert the copy before the argument. It's not like trying to copy the argument before it's emitted is going to break anything. If anything, the copies go where the phi is, or in a separate block. But that's the corner case you don't want to deal with right now. So we're going to need insert instruction after. So do you think A should go after B or B should go after A? Insert instruction B. Let's just insert instruction A after instruction B. Okay. So it says, you know what I think? They should probably not be called A and B. Well, what should we call them then? You're just telling, you're doing the thing. Everything I write, you're like, that's wrong. If you have a suggestion, I'd love to hear it. Just call them inst and after or something. That's so much worse. That's so much worse. A and B is so much more easily distinguishable. That's A, that's B. Insert instruction A after instruction B. I think it's clear. Not A or not B. Return. Get out of there. Okay. Otherwise, A next should be equal to B, right? No, B next should be equal to A. B next equal to A. That would make it clear which one is which. What is inst? Inst stands for instruction and after, but I don't, if, like memcopy, they just, it's not like they called it source and dest. I understand that tells you which way it goes, but it's not like it matters, because it still is confusing and people get it wrong. A and B is so much clearer, and yet you still refuse to call the file ir.h. Because it's fucking confusing. I still don't get how you get that. When looking at er.h and raw.h, it's scary. You go, I don't know what those are. And I have to click on them, read them, and then try and figure it out for myself or hope it's at the top of the file. Or you can just name the file what it is instead of confusing everybody trying to learn your code base and having to tell literally every single person, oh yeah, array.h is for register allocation. It's not just intuitive, especially unless you're like already a compiler developer. And one-letter variable names are not confusing? No. Then just name the parameters what they are. Same argument, really. They are A and B. They are very clearly defined. Instruction A and B. A goes after B. I'm not going to have this argument with every 5 things I write. I'm just not going to read Twitch chat again. Jesus. I've literally wrote 20 lines, and at every stop, you're like, oh, this is wrong. This is gonna be bad. This is wrong. You should name those differently. You should do this. Come on. I get it, but come on. I'm a person. I'm just writing code. I'm not some genius. I'm not gonna get it right first time, first try. I'm not teaching you how to do this. I'm just writing code. So that's what I'm gonna do. I'm just gonna write code. So we would love to set B next to A. And we would love to set A previous to B. These are 2 separate things that we would like to do. Previous. So B next is A prev is B. So this means that after B comes A, before A comes B. But if there was already an A previous, well, we want that to be B's previous, but we have to do that before we overwrite A previous. So we have to do this. B previous equals A previous. Is this correct? So we are inserting instruction A after instruction B. That's probably not correct. We're probably going to want to set A previous to B previous instead, right? Instead of B itself. No, A comes after B. I'm getting there, don't worry. Doubly linked lists. So if A is after B, then A previous needs to point to B. B previous needs to point to whatever it did before. So B previous can stay the same. We don't need to change it. Right? B next needs to be updated, but whatever's before B can stay before B. Whatever's after B is A now, but whatever was after B needs to be A's next. So that's where this pattern comes in. Whatever was after B okay, A next equals B next. So A coming after B now means that whatever was after B goes after A. So we basically have 0. How do we do this? 0B1. And now we have 0B A1. Sure. A next becomes what was B next. B next becomes A, and then A previous becomes B. Okay, and then B next previous. Okay, here we go. So we're going to say if B next, right? Okay. And if B next, then this means that B has stuff after it, and that means that its previous needs to be set. Otherwise, the doubly linked list will be broken. So the next's previous is actually, whoops, it's actually equal to A. That tracks. So now B next points backwards to A, previous will always continue to point forward to B. And then the B next gets updated to A next gets updated to B next. Okay, we're good. We are good. This should be a full insert instruction after, right? Does this make any sense? We'll peek. Nothing. We're assuming it makes sense. Insert instruction after. Okay, so insert a copy instruction after the phi, which will basically just ensure register allocation is correct, I'm pretty sure. Because it'll say that the phi argument becomes the same as whatever its value is. So they'll be allocated the same register. Okay. So now, here's the thing. We now have to keep track of all of our uses. So remember in intermediate representation, hopefully if we didn't keep track of our uses, it's going to be a whole mess of refactoring. Did we have mark used by? We don't have used anywhere here. So we didn't mark used, which is a horrible thing to do that we're going to have to now go through and do. But it's fine. It's not going to be that big of an issue. So basically, there's honestly only 500 lines. It'll be quick. You know, a quick 500 line refactor. Not too bad, not too bad. Where does it actually start? Okay, phi argument. Okay, so do we even have a place to put them? We don't even have a place to put them, I don't think. Let's look at our IR instruction. We don't. So we're gonna have a singly linked, we'll just call it list of uses. And then this is going to be what? Instruction IDs? Instructions? Ookie. So list of uses, sorry about that, had to answer my phone. List of uses, instructions that use this instruction should go in this list. I think that's pretty simple. So we're just going to have a list of uses, which is basically just going to be a list pointer. And we're just going to make a list. Where can we make this list where it doesn't make everything kind of insane? So we're going to have a use defined. That seems good. It's going to be a struct. Can't forget that. Can't forget that. Okay. So with a use, what do we have? We have basically an instruction that is being used, or, well, an instruction that is being used, but the uses are stored within the thing being used. So we don't have to store that. We already know that. So instead of the thing being used, we're storing the user. Okay, that makes sense. And then it's going to be a linked list. So we have a linked list of uses, and each of them contains a user. Should we keep track of like where the user is from? I think the instruction does that already. It's fine. So now in the IR instruction, we should have a valid uses, okay? And now we're basically gonna have to do the mark used thing. So we're going to have to mark an IR instruction as used. So this will be user UZ. Okay. So user, whoops, classic. User is going to be added to the UZ's list. So maybe UZ should go first. I think that makes more sense. Okay. Mark used. And we're just going to put this at the top. Whoops, we'll get there. Okay. And mark used, we're basically going to go find the last use. Okay, so we're going to say if UZ uses, right? This means that all we have to do is find the last use and add to the next one. We don't even have to do that, actually. We can just add to the head of this list every time. So we can say UZ uses equals some new use. This is such bad naming, but there's not really a better way to do it. So A and B might be better at this point instead of UZ, user, and use. Okay, so we have mark used. So the UZ uses is going to equal a new use, right? We're going to have a use pointer, which is going to be new use, be allocated with like malloc or calloc or something like that. We'll use calloc and then use. Okay. UZ uses new use. So UZ gets a new use added to it, new use. So then we just have to say new use next is equal to the old head of the linked list, and then the new use value user, right, is equal to the user. That should do her. That should add a new use to the IR instruction. We should probably have like a print uses thing as well. Why did that happen? Okay. Mark used. So that's mark used. Now we have to go use the mark used. So when we create a new phi argument, we know that the phi argument itself isn't, that's something else. That's not an instruction. This is an instruction. So when we have IR block attach, okay, that's still not correct. When do we create instructions? IR immediate, okay, doesn't use anything. Immediates can be used, but they don't use anything, do they? They're just an immediate, yeah, that's it. A load has a reference to an IR instruction address, which means that the UZ. So what's using? Is that correct? Yeah, the UZ. So what's being used? The address is being used, and the load instruction we created is using it. So address is used by load. Okay. And then this is a function name. So anywhere we see an instruction in the parameter, we can go ahead and assume there's a use. Okay. So mark used, an indirect call, uses the function that it is calling. I'd say that makes sense. Oh man. Okay, indirect call. Now we have load global address. Load global address, nothing. We have a load local address. So we can now mark used. on local, which is used by local address. When we load a global, nothing's used. When we load a local, we are loading a local instruction. So we can mark used on what? Local. It's used by the local load. Makes sense? When you load a local, you use the local. So here we have source. So source is used by the global store. What are we storing? Source into a global variable. Okay. Here we have two uses, if I'm correct, in a local store, where we use the local and the source. Very cool. So we use local in the local store. You know, going to Walgreens, going to the local store. And then we also have source. Can you hear my voice going out? It's amazing. Happens so fast. Ooh. Okay, where are we at? Store local. We still have to deal with store itself. Branch conditional. Okay, so the branch is going to use the condition. I guess only the condition. I don't think we can really use a block in any sense of the term. So condition is used by branch. Hey, look, IR copy. Probably gonna have to make that. I think we kind of already did. Where were we? So instruction copy, IR copy. So what we could do instead. Also, we got to set the copy value, do we not? Copy value, reference. See, all of this should just move to that function. And we can call it, say, IR instruction copy equals IR copy. Okay, reference equals source and yeah, we'll go with that. Wrong place again. Return copy. Copy will not be self-inserting. I don't know why I put a underscore there. Copy that to IR return as well, which appears to not self-insert. Okay, so IR copy just creates the copy thing. And we would like to create a copy with what in it? Do we have context? I'm probably going to have to do like info context. We don't need it. It's not used. It's not used in a majority of these, honestly. We could probably get rid of it. And we probably will. So then we just need to pass in our source, our reference. What would we like to copy? I'm pretty sure we would like to copy each of the phi arguments. So this would be argument value, would it not? Yeah, phi argument value. Okay, so for each argument, insert a copy after that copies it. That's right. That's why we did all this. Because now, guess what? Why are you mad? It's implicitly declared. No IR copy, huh? There you go. IR copy. So IR copy now exists, and we can now do our mark used. And we would like to mark, first of all, the argument used by the copy. Right? I think that's right. Okay. So then we need to mark the copy used by the phi, right? The instruction. The actual instruction that we're within, that is a phi instruction. And now, here, this is kind of more part of the next thing. Now we need to set, so replace the uses. Oh man. So I'm just going to read what I have written in my notes. Replace usage, just use. Replace use in phi of original phi argument. It now uses copy. Replace use in phi of original phi argument. So to me, this means that I'm going to need like the to iterate over uses, right? So I'm going to have like a use pointer use. Sure. This is going to equal argument by argument uses. That would make sense. Okay. While use is a thing, use can be equal to, yeah, just use next, right? It's a linked list. Okie doke. Okay, so for every one of these uses, replace use in phi argument. It now uses copy. Okay, okay, okay. So, if use, right? If the user that it actually refers to, the phi argument user, is, I'm getting it now. We have to update the use that was already created. Okay, okay. So if use user is equal to the current phi instruction, does this make any sense? Then we can say, what? We basically want to remove it, right? We just want to remove it from the list. So removing the original use that we added when we created the phi, is that correct? You need to, Sir Aid, you need to replace each reference to the argument with the copy, basically. And by reference, I mean pointer, yeah. So replace each reference to the argument with copy. Yeah. So the fact that the user of this use was this phi instruction, then that means that in this use, oh man, this use has to be removed from the upper list. So we need to, it's a linked, singly linked list, so we need to keep track of previous use, which equals null. Okay, and then here, is this allowed? I think that's allowed. It's not like the best, but I'll deal with it. Okay. This is so ugly. I love it. But replacing an argument of an arbitrary instruction is going to require a switch case on every instruction type, I think, or something like that. That's a comma expression that is allowed. Lit. Okay. If use user equals instruction. If previous use, right? Else. Whoops. I'm getting there with the new keyboard. So if previous use, then that means we just have to say set the previous use next to this use next. And we've skipped it. Otherwise, we have to set our original argument uses, the same thing we initialized to, argument, equal to this new use. Because if there is no previous use, then it means that this has never been run, which means we're on the first iteration. We could also just unroll this loop and have the first check out here and take this out and yeah, don't really want to do that. This is fine. So we replace the use in the phi argument. Oh man, does this make any sense? So this phi argument is used. One of its uses is in the phi instruction. So this phi instruction use no longer has this use, it's using this use. Oh God. I think that makes sense. I think that makes sense. So this is going to be remove use of phi argument in phi. It's now used only in the copy. I shouldn't say only, it's now used in the copy instead. Yep, classic. Okay. Yeah. Oh. Then I have to switch the actual phi argument. Did I never do that? Okay. So we're gonna have to do this. When should this happen? Should this happen for every argument? So should it be like after this? Is this correct? Could also maybe do this. Is that clearer? I think I want to update the pointer though. Is that a pointer? This isn't a pointer, it's a union. So this is just copying. No, this is a pointer. This is the, yeah. Because this isn't the instruction. This is actually the phi argument. Okay. Okay. I think that's good. Phi to copy. It's a very basic one and probably wrong, but it doesn't matter. We're gonna see if it works. I think it will work, at least for our use case right now. So after we run phi to copy, can we do IR emit? Something like that. And then in the backend, we can just say, okay, we're gonna need one of those register allocation thingies. Also, that means we're gonna need to go include it. This is a little small in this file. Perfect. And this is going to equal, we'll just call it RA info. Is that the name of the function actually? What do we call it? Equals RA underscore. Yep. RA allocate info. Okay. What do we need here? I think I can turn on company mode. So we need context. Should be easy. What else? Result register. That would be racks. We need general registers count. There's 13. Do we have that? What does register count? Probably like 17. Oh my. Okay, hold on. Yeah, so that's going to be all of them. So we'll add something in here. Oh my. General register count. Is that okay? 13? Is that correct? I don't even know. It's fine. Maybe that should be in the header. I don't even know. So general register count and argument register count, these are all going to be needed. We'll see how this works. We'll see how this works. Let me see. Pretty sure I've tried before. Okay. And we're basically oh yeah, another thing we're going to have to do. That does remind me. I'm going to do the same thing as earlier. Put this up over here. Classic. Okay. Yeah. Okay. Sorry about that. Sorry about that. So I think argument register count we can store somewhere else because it's going to be different per format. But the general register count will never change, so that can be a preprocessor define. In any case, we can put general register count here. And then put general registers. Okay, so we're going to need a register array. Right, so this is going to be general. And it's going to be general register count. Is this allowed? I think this is allowed. And then should we have general register count +1? No, I think just general register count. This can be all the general registers, right? So we can say reg racks, reg rbx, basically everything except the 4 important ones are, I guess, source and dest. We're going to have dx and cx. So ABCD registers, source and dest. Does it go to numbers then? Am I forgetting some? What? There we go. Also, I did that totally wrong. But I got there in the end. Oops. I'm good at this, I promise. New keyboards are fun. Probably don't want to use all of these, but this should be fine. Why this is written in C and the OS and C++, so this to exercise you in different languages. It turns out humans are capable of knowing more than one thing at a time. I know Twitch chat has a hard time comprehending that, but they are actually able to be like fully faceted human beings that don't just do one thing, like play Fortnite. So yeah, I write things in whatever language I want to write them in. And C was the one I wanted to do the fun compiler on, with no dependencies, so that everything is completely from scratch. Okay, so we have general registers count. General. We have argument registers count, which is going to be like a whole thing. Could probably even make it a define. I think that's fine. I mean, it's going to be different where we can't make it a define. Context. Is it format? Call convention? That's it. CG. Call conv. I remember that one. We'll just do a switch. Context. Call convention. Equal, yeah. Case. CG. CG underscore call conv. So if we have count, whoops, count, then this is going to be, do we have panic? Forgot what it's like. Is this it? I honestly don't remember. Okay. So panic with invalid call convention. Good enough for me. Okay. And here's the thing, we're just gonna make that the default as well. But when the case comes to CG callconv Linux, I don't think panic ever returns, but you know, we'll handle our cases. And case CG callconv mswin break. So Linux, we have certain argument registers, and on others we have a different amount. So we're going to have a register pointer, argument registers, which is going to just be equal to null, so we don't trick ourselves. And then we're going to say argument register count is going to be equal to 0 by default. Beautiful. Here we can update the count to be, what is it, 6 on yeah, 6. Is it 4 on mswin? I don't remember. We're gonna have to look this up. Let's look it up together. Okay. Panic does not return. That would be quite horrible. It calls exit, and as we all know, exit always terminates the current process. It's not like we've ever had a problem with exit not terminating the process after all. Never, not once. Okay. mswin has 4 argument registers. That's what I was just looking up. Yeet. And then Linux calling convention. What is it? system calls and user space functions, kernel interface. System call convention has di, si, dx. Okay. What? Okay, where am I going? Here, here. And then we're going to copy these here. And we're going to change that to 4 as we now know. I'm going to say argument registers equals when argument registers. And then this is going to be Linux. And we're basically just going to say argument. This is horrible, by the way. Yeah. Probably a better way to do this, but I'm not the one that's going to do it. Registers is going to be a register array. Okay. This may have to be a define. That one. And equals bleh. This can be reg, what was it? RDI. RDX. RCX. 8. And 9. Beautiful stuff. Syscalls on Linux use R10 instead of RCX and clobber RCX and R11. Consts are not constant expressions. Coolio. That'd be a confusing one. And on Windows, they are CXDX89. Okay. Okay. There we go. Nearly. I swapped the wrong ones. I'm a genius. Go forward. Nope. There we go. It's a confusing one to use, but it does work. So we have 4 registers, 6 registers, DISI, DXCX89, CXDX89. Then we set them accordingly. Okie doke. So now we can just say argument register count and argument registers. What else do we need? Egglet, hello? Okay, let's go check. That's it. So that should be all we need. And then we can just call RA info. And then we can hope and pray. Now that's good. Okay, cogen count doesn't exist. It's conv count. That's something we can fix at least. Okay. 1,300 lines of errors, not too bad. MS when argument registers doesn't exist. So there need to be semicolons here. I have a feeling. Nope. We'll get there. We'll get there. What's the first error? Unknown type name register descriptor, register pool. That's fair. They don't exist anymore. Implicit. Okay. Here's the thing. These are all going to have to change. All of these, yes, I know. So register descriptor is really just register now. I don't want to touch all this stuff, really. Unless I absolutely have to, which it looks like I do. So, in replacing all this register stuff, we can get rid of this whole register pool thing, which is going to be nice. It's going to be very nice. Because we can literally just yeet all of that. We'll get there. We will get there. So currently it's complaining that register descriptor doesn't exist. What if we just went and added that back? Remember when we took all this stuff out? We change register from a struct. We go, nah. Register is an int, just like register descriptor. So we want to get rid of register pool and register descriptor. These we want to keep. Nearly there. 1,000 errors, 1,000 lines of errors. Field name not in record or initializer, dot in use. Okay, there's a whole bunch of register initialization stuff. We don't need to do that anymore. So do we still need the register struct for anything? What was this for? It's slightly confusing. I'm not sure if we need the register struct anymore. I think you can yeet them. Okay. See, we're still going to need the name lookup function, though. We still need the names, yeah. So the names, do they require this? I don't think they require init register. Yeah, it's not used here. Okay, we're good. So now we can get rid of, what was it? I don't even know. Let's look. Hey, 50 lines of errors. We got rid of 1,000 lines of errors there. Warning, implicit declaration of init register. Don't do that then. Okay. Looking better. Request for member in use is something not a structure. Prepare call x86-64. Guess what? We're just not going to do it. What is the problem? Excess elements in array initializer. One of these things is not like the other. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Which one of these isn't a general purpose register? I don't know. Should we just bump it up to 14 and not care? To do. This should probably be 13. Sounds good with me. The next argument register count. Ah. upcase, that's what it is. Jesus Christ. Just call upcase. That was rough. Okay. Nearly there. Undefined reference to array allocate info and array. Oh, okay, so CMake now. Needs array. Okay. Hey, it ran. Well, I mean, we didn't crash. We did exactly what we did before. That's kind of pog. So in register allocation, we call f_emit, but we're probably not calling that correctly. Are we returning info? We never returned info. That's what our issue is. Whoops. Okay. Do we print it twice now? We print it twice now. Pog. Is it different? Let's see. There's a phi argument. So 32, 25, 14. So let's look at BB3. BB3 didn't change. Did anything change? Huh. So we're probably going to have to check if something is the branch first or not, and stuff like that, or the last. Like a block first. Because if you replace the first one in the block, you need to update the block pointer as well. Do we have any copies? We don't. Do we think we have any copies in RA? Are we saying, oh yeah, we inserted a bunch of copies? Or are we not inserting any copies? Okay, so to do. Handle beginning, end of block function stuffs. Okay. I to copy. We call RA info. It is happening. Instruction type equals copy. Do we know how to print a copy? No. So what do we do on the default? Handle IR type. Did we see any to do? I don't think we did. So why'd IR copy go through? That's an f_emit instruction. So maybe we're just never trying to omit the instruction. It would be confusing because we're doing all this stuff. So let's printf found phi. I think that's reasonable. Whoa. Oh, I'm in symbols. Okay. I don't see a single found phi, to be honest. Not a single one here, which is interesting. Did I screw up the iteration? What did I do? So for every function, for every block, for every instruction. Maybe I never set cogen context when I created it. Did I? No, I set. That's interesting that it wouldn't even think of it as updated. because we do all this updating. So insert instruction after. Maybe it just has to do with being at the end or the beginning, you know? Okay, so if B is at the end, that wouldn't really make sense. We want to insert before, because the branch has to be at the end of the basic block. That's what basic block means. So let's think about this. So we never have a found phi somehow? Is it like, am I running the wrong one? You know what I mean? Do I somehow have some other one being run? That's in this directory. But there's nothing being printed out. So it's like phi to copy isn't being called. Which this is being called, so, right? I don't IRF emit again in back here. Yeah, I just call RA. So this is being called, but this isn't working somehow. Phi to copy, please. I'm gonna keep waiting until I can find out where the hell the code is executing. We have hello. What did I do wrong? So we have hello. We have not function. So is all functions incorrect? Is this like never set? That should be the first function, no? So it seems like a problem with code generation itself. We create a code gen context. Are we? And then we code gen the program, which code gens the expression. Which may be a function. Okay, here we go. So we say IR function create. So how do we create main, for example? Where's main? Main. Context. Right? All functions. Whoa. Should be equal to main. Okay, that's much better. We definitely broke things, right? Handle IR type 7. Okay, so now we have an assert running. This is good. This is all happening. We have found a bunch of phis, and we can't print it out, is what we've realized. So we're just gonna slap it in here. Copy. Oh boy. Break. Print to file. Probably just the ID. Oh yeah, that happens right below as well. And then we could, oh, yep, I'm good at that. Okay. And then this would be %zu and a percentage to actually get a percentage sign. So that's percentage and then the number. There's a break, but it says global address still. should actually equal copy. Very nice. Okay, we have to set IDs again before emitting. Okay. Oh, yep, I'm good at that. Not too shabby. So we have function 1, which got no copies, function 2, which got many copies. So you can see 15 is a copy of 14, and 15 is now used in 40. These can't be correct. I'm convinced they're not. So yeah, we now have a copy in front of every branch, which effectively means that I'm not exactly certain. But I know it is necessary because I wrote it down and I was very vehement. Okay. I think that's good. We're ready for our next pass. How about the call arguments? More specifically, function call arguments. Right? Nope. Okay. Function call arguments is basically going to insert copy instructions before each function call, which copies all of the arguments into the proper registers, if that makes sense. So this is kind of like pre-allocating function call argument registers. So let's do it. We have to do our same little ditty as up here. So I'm just going to copy it. Whoop. I'm just going to copy it. And then get rid of the body, which is going to be this big if phi. Right? And then this is going to be if it's an IR call. Would you look at that? Okay. Now, what are we going to do for each call? Well, we're going to have to go through each of its arguments and insert something before the call, which means we're going to need insert before, by the way. Insert instruction A before instruction B. Well, before. Okay, A and B. So we want to end up with A. Something like that. Kazanis says, what's up? What's up, Kazanis? How's it going? Okay, so... Oh, by the way, I found a bug in insert after. Nice. If B prev B previous next is going to be equal to B. B prev is going to be equal to A. A next is going to be equal to B. And a prev is going to be equal to b previous. So a previous equals b previous. This equals here. B previous next, if it exists, equals a. B previous equals a. So we have a previous, previous next, B previous, A next. That should be it. I think that's correct. Saraid says, it's the same bug that we had in free. What? Castanis says, slowly. Lamau. Insert instruction A before instruction B. Saraid says, you need to update the head of the list. Yeah, I know. We have the to-do here. Handle beginning, end of block function stuffs. Probably important. I agree. I.e. the first instruction in the block. Yep. Remove use of phi argument. Yep, so that's function call arguments. Okay, so now if we get a function call, we're probably going to want to loop over all of its call arguments, right? So if I remember correctly, we have like an IR call thing, which I think just resides in... There we go. So the instruction value call arguments. Okay, so it is an IR argument thing. IR call argument. Arguments equals arguments. Okay. Arguments equals arguments next. How about that? And then the instruction argument can actually be equal to arguments value. Okay. Good, good. So for every call argument, we are going to want a new instruction, arg, which is going to be an IR copy. This will be arg copy. Arg copy is a copy. Its value. See, I'm doing the wrong thing again. IR instruction arg copy. Could we not just set the result register of the argument itself? Probably could. I'll get there, don't worry. IR instruction arg copy equals IR copy. Of what is it a copy of? First of all, we're going to need to feed it context for no reason, and then we're going to have to spit in IR copy info context copy of argument. Insert instruction before. Now I'd like to insert instruction A, arg copy, before instruction B, which is going to be instruction, our call instruction. And in here, here's also what we're going to need to do. Size ti equals 0. This will be familiar to you. And then we can just plus plus I in here, which means, what does this mean? Yeah. Okay. So then we're basically just going to want to use our little table. Okay, yeah. If I is less than info argument register count, here we'll check for an error. If I is greater than or equal to, then we'll say, I guess just panic and say, I guess this should be a to-do. We have to-do, don't we? Handle stack allocated function parameters somehow. I mean, maybe we don't even have to, maybe we just skip them and don't insert a copy. You know what I mean? Maybe, or maybe we insert a stack allocate. I don't really know. We'll figure it out. For now, I think a panic is completely fine. And then else, right? We're going to want to insert the instruction, but only after assigning. So our copy should get, see, it doesn't have a result either. That's going to be an issue. So we're going to go to here and add something to the IR instruction itself, which is going to be, this says register allocation. I'm just going to add a register. Maybe, oh yeah, I remember now, because we need to make a flat list. Size t, this will actually just be a register result. How about that? So now we can say that the result is equal to info argument registers at I. So we have the argument copy set to the proper register, and then we insert that before the call instruction, and we do that for every, yeah. I don't think this is insane. I think this would work. You want to try it? We're trying it. Okay, let's see. Hey, it worked. See, now what we have to do is mimic the intermediate representation printout, but add in our registers. So what we're going to do is say if instruction result, because we're going to have to make 0 an invalid register. Actually, let's go do that before I forget. 0 is an invalid register, so we have to do reg underscore none. How about that? Okay, so now if instruction results, we can just print out our lovely thing like this. We're just, basically I want to do the same thing. So maybe let's just try something like this. What is the, so let's just copy ID width, length, and difference, and put that in here. So this is going to be results. Lots of renaming. result length, CU, pipe, and this is going to be instruction result. Maybe we can make this like 4. Well, let's see, this is 1, 2, 3. So let's make it 6. Difference, we'll call it result difference. And then we can say result width minus result. We're going to cast this to a size t. So we should probably just use a different specifier. And then ID format we can have be the same as up there. Even just do the same. Like this. Okay, not bad. Not bad at all. That means I can also just undef right after. Put it outside, because why not? And then this is result format. Okay. And we can move this undef way up again. That one. Okay, so now, if there's an instruction result, it should be print out. Which means if any register allocation is done. And you can see that it's beginning to happen. We could also just say else. Printf a whole bunch of spaces. Right? Something like that. There we go. Now everything lines up. Look at that. So now whenever we have a register allocated, you can see that it's allocated right here. And you can see that these copies for these parameters are actually, also we didn't update the function call. that's a problem. These copies are actually allocated to the proper registers, given that this is RCX and that's RDX. What's going wrong now? Register allocation. We had function call arguments not updating the actual argument. Yeah. So argument's value is actually equal to the copy now. Does that make any sense? So now, yeah, you see we call, on 8, we call 3, which is global load of GCD Euclid, a function with 6 and 7, which are our copies, with the proper registers allocated. Hey. Poug. This is not going too bad, huh? This is not going too bad. So with our function call arguments now properly allocated, or pre-allocated, I should say. Yeah, this is probably when it's going to get complicated. Okay. First of all, we should just handle one more thing. Oh, I'm in symbols mode again. Function return values. So return values go in a specific register that we do have to handle. Nope, red. register. Okay. Function return values. Yeet. Should probably just have a driver that calls something on every instruction and then call that with different function pointers to all these different passes. But again, we'll get there. So we have this for loop, right? Yeah. So if it equals a call, no. I think we can just go through each function. I don't think we even need to go through the instructions. Is that correct? Okay. Because our return value is actually just here. And then we can just say, bud, this is a copy. We already know where this should go. This is a, this is a return value. This can just go in the result register. We cool with that? You can now see that this 5, for example, is stored in the register 1. How about that? And same with this function call, which is the return value of the main. The main of main. Wow. Okay. So there you go. Function return values are now properly allocated. And, okay, what else do I have in the notes? Collect a flattened instruction list. Okay. So we're going to have something like this, I think. I think this is the way to do it. Instruction list. And then this is just going to be instructions. Right? Yes, instructions themselves are already a linked list, a doubly linked list, in fact, but what we'd like is a flat list, a flat singly linked list, which we could even make an array if we wanted to, or a vector, but we'll get there. I don't really care. So this IR instruction list is going to be collect instructions. I'm just going to collect all of them into a little list. Okay, and this is going to be collect instructions. IR instruction list. And we're going to need an IR instruction list struct. And if we want to use it like this, we're going to have to type def it. Define it like that. It's going to be an instruction pointer. And you guessed it, Frank Stallone. Nope, an IR instruction list next. How about that? So collect instructions. We're going to create an IR instruction list pointer, which is going to be list, going to equal null. Oh, yep, I'm good at that. Open Feedback Hub again. Microsoft, give me feedback. Okay. This is a pointer. Return list. Okay, so now we basically want to loop over all of the things and put them into the things as long as they are things. It's my eloquence that boosts me forward in life. We are going to need the info thing. Otherwise, it'd be quite tough to know what the instructions are. Okay, so now, right, we're basically just going to switch on instruction type. And we say, basically, add instruction to flat list if instruction needs register allocated. So any instruction that actually has a result that needs to be stored in a register should go return, should add the instruction. Otherwise, it'll do nothing. Okay, so to add the instruction to the list, we're just going to update the head. Well, that would mean it's backwards. So we're going to actually do something like this. We're going to add to the end of the list. Oops, what did I do? Okay, so we have list and list it. Sorry, I just had to check something. We have list and list it. And we were going to say list equals, I guess, calloc, a new list thing. Yeah. But really the size of that. And then one of those. So this will give us a zeroed out list. We can then say list instruction equals instruction list next equals list it. And then finally list it equals list. So next time around when we say list next, it equals that. But the first time around it equals null. Woo, I think that works. See, now all we have to do is say print instruction list, IR instruction list, I am not good at this yet. Okay, print instruction list. And we basically want to say while list. We can even do a for loop. Right? And then we just say IR femit instruction to standard out. And this will be list instruction. Now we can collect our instructions and print them out, hopefully, somewhat legibly. So instead of doing this, we're going to do print. Yep. Okay. Didn't quite work. It just didn't print anything out. Is that correct? How does that work? So maybe somehow we're returning null putter or something? Ah. I mean, that shouldn't be an issue. But this will. There's no case. Lamau. I was like, why isn't it working? Probably because there's no cases where you actually said it should do anything. Okay, what needs a register? What types? I'm pretty sure an add is going to need a result. Same with a sub. Tracked. Okay, we spelled them out. Good to know. Anything with load in it is probably going to need to load into somewhere, right? So local load. Local address. Pretty much just everything goes here, right? I'm in symbols again. I wonder if I have a good list somewhere. Okay. So we have load. Isn't there global load as well? There is. Is there global anything else? Global address, yes. The address needs to be stored somewhere. Function call. I mean, they're kind of pre-allocated. Copy would definitely need a register, right? I may just be butchering this. What IR instructions need registers? An immediate. Comparison. I don't think stores need anywhere. Does a local store need a register or a global store? All instructions that produce a value. Exactly. I'm just trying to think about which ones do and don't. A call probably produces a value. Case, IR, bleh. What else do we have? I don't think branch. I don't think return. That's also a branch, or branch conditional. I don't think any of the stores we need. Yes, yes, no. Yes, yes, yes. No, no, no. Question mark? Yes? Probably yes. Yes, yes. Yes, no, yes. Yes, no, yes. Yes, yes. So parameter reference is a confusing one. We're probably going to have to pre-allocate params, no? They do need it, but they're also pre-allocated, no? A stack allocation doesn't need it. I haven't even created stack allocation instructions, have I? Lamau. Where are we at? Hey, that's better. We get a flat list. So now you can see it is in reverse. Oh, because I did the list iterator stuff. I totally forgot why I did all that. So we should say list iterator, list equals the new thing. Okay, here's the thing. I want list iterator to refer to the end of the list, and then I want to add to that. So I want to say list it next equals list. I did this a bit backwards. Okay. So list it next equals list. List it list. Okay. So we create a new thing, and then we say add it to the end of the list. But then this means list gets changed. Does it not? Yeah, list gets changed all the time. So this has to be like another list iterator thing. Can I just do this? No? This is horrid. List iterator next instruction. List iterator equals list iterator next. I did something very wrong. Okay, hold on. Because list it starts as null. So we're going to say if list it, do this stuff. else you're going to have to do some other stuff, which is basically just going to set list it itself. Did I screw it up again? I did screw it up again. Okay. So if list it, dereference it and set the next one to a new thing, then update it. Then we update it. The one we just allocated, we update its instruction. And then if list it doesn't exist, if it's null, like it should be at the beginning, then we just say calloc and set instruction. So the next time around, list it will be true, list it next, list it should refer to this. My terminal prompt has this abomination, /033 138 279 151 215M. Oh god. I'm not sure I'd want to implement RGB support in the terminal driver. Well, you underestimate my power. List it. What did I screw up here? Oh, there we go. Cannot insert null instruction. I don't think insert is the proper error message. Yeah. Cannot emit null instruction to file. That'd be a little better. So somehow we're getting null again. Why am I an idiot, man? So list it next equals something new. And then update list it to that new thing. And then update the instruction, this new thing. Ah, there it is. Fixed it. Rough. Okay, there we go. We now have our list of stuffs. So you can see that not all of them are here. For example, 9 is missing, and 22, and what else do we got? 32, and 45. But all of these will all need a register assigned, and you see some of them already do. We are now at the time where we can start doing complex maths. Isn't that fun? Okay, so with these instructions that we've collected, we need to build an adjacency matrix. Fancy, right? Begin instruction lists. This is actually end. Don't worry about it. Boing. Boing. We're going to eventually move these to new files. Okay. So it says, oh dear, haha, matrix time. Yes. It's honestly not as bad as it seems. And again, when you have to say something isn't as bad as it is not that bad, it is that bad. So, you know, it's not easy. Oops. I'm an idiot, man. Okay. This is where we're at. We're gonna need like this struct, which is gonna be like an adjacency graph. Okay, and this is just gonna contain everything because there's gonna be multiple iterations of the data, and this is just gonna contain it all. One of the things in this graph will be an adjacency matrix. Okay. Okay. And then we can just call this matrix. We can create an adjacency graph, G, and then we can set G matrix to build adjacency matrix. Just going to take in info. And also instructions, right? We need the flat list of instructions for this. Am I correct? I think that's correct. We'll see what we end up writing. Okay. Let me think about this. Where are we at? Yeah, so, okay. Oh, also, we can keep track of the size of the graph in case we ever need that, which is called the order in mathematics. So the order of the graph will be the size of it. And the size of the graph will actually be how many registers there are, correct? I'm pretty sure. Pretty sure that's how that goes. Copy this. We're going to say build adjacency matrix, which we will return an adjacency matrix. Is that how that works? Do we need a pointer? And we will just try our best to build one and return it. Okay. And then IR instruction list. Instructions. Okay. Now, an adjacency matrix basically is a square matrix where the indices into each of the two dimensions, right? It's a two-dimensional array, you can imagine. So if you had 0, 0, and 0, 0, we'll just start with something as simple as possible. Then usually they're top left indexed, it doesn't really matter, but we'll go with top left index for now. This is 0, 0. This would be 1, 0 if it's xy. This would be 0, 1, and this would be 1, 1, right? 0, 0, 1, 1. And the thing is, an adjacency matrix will say, okay, at 0, 0, that means that if this bit is set, or this thing is non-zero, or, right? If this place in the matrix has the value that you want it to, then that means that these are adjacent, and that means that two nodes, or vertices, or indices, or whatever you want to call them, in the graph are actually adjacent to each other, which means they have an edge connecting them. Does that make sense? Hopefully that makes sense. So how do we actually implement this matrix stuff? Let me think. Let me look at my notes. Yeah, okay. Yeah, why not? So what we're gonna do, and what I've done before, right, is we're gonna say, I'm tempted to just pass in the adjacency graph and just set the matrix based on this data in build adjacency matrix, but we'll see. We'll do that. So we're just gonna say info, instructions, adjacency graph. Call it G. Okie doke. So build adjacency matrix. Basically, the matrix itself is just going to be a bunch of bytes in a row. At me, I know. So the adjacency matrix is going to have a single byte or single char for every single entry in the matrix. And this could obviously be optimized to be like bit fields instead of in bitwise operations, instead of entire bytes for Boolean values, but it's fine. It really is fine. So we're going to have adjacency create, right? So we'll have adjacency matrix, adjum, sure. And, whoops. This is basically just going to say allocate an adjacency matrix, right? Yeah, so there's going to be some size that we'd like to create this at. And that's going to be the size for our data. Adjacency matrix, M is equal to calloc. No, it's not. M dot data is equal to calloc, one size of size, not even size of, just size. Please get me size bytes. Then we can just say return M. Okay. Okay. And then we can just say char putter, adjum entry. This will get us a pointer to within the data where this entry actually resides, which means we're going to need like an X and a Y or coordinates or something. So it's going to be within some matrix. It's going to be, and then we're going to need coordinates. So should we do like, we have entered the matrix, Neo. M.data. So this is basically going to return the address of m.data at y times, y times, so yeah, we're going to need to store the size as well. It's just going to have to happen. Okay. Plus X. If you don't know, this is some basic two-dimensional array indexing where the Y, how far down you are, is multiplied by the actual size of each row, which means that this is the actual amount of elements in all of the Y rows that we would like to skip. And we skip all just past those, and then we skip past the number of X elements into that line to actually get to the proper place. And then we're also going to get adjum. I think just adjum would be good, right? I think that would be like return if they're adjacent or not. I think that's worth it, which would just return this. And we're going to need a way to set these stuff. So we're going to have, adjum set, which is going to be something like this. And adjum clear. Okay, so adjum set is basically going to say m.data at thing, right, is equal to 1. And this is going to say m.data at thing. Here, instead of doing this math over and over, what we can do is actually use adjum entry on mxy and then set the data there by dereferencing it, or clear the data there by setting it to 0. That's much better. And this can do the same. So now everything is based on one adjum entry. How about that? How about that? Okay. When are things adjacent and when are they not? Right? That's something that's interesting. Oop, yep. Me using the Windows key when I shouldn't be. Me using Alt when I shouldn't be. There we go. So matrix should already be a member that has memory allocated. So we can say matrix, I guess when we say adjum create, it's just going to copy. That's fine. So we're going to create of order. Is that correct? That may not be correct. How big of a matrix do we actually want to create? Let me check if I mentioned this anywhere. So when we build the adjacency matrix, how big should it be? It should probably be the same as the graph order. But they're, yeah. Oh, wait, no. No. Here's the thing. Yeah, so the adjacency matrix is actually between all of the different instructions in this flat list. So it's actually the size of this instruction list, which is kind of insanity. How do I get the size? I could keep the size. Or I could use that index. That's right. Okay, so then when we create a this list, right, we can just set the index. I don't feel like it'll be that crazy. Good old O(n) squared efficiency. I mean, it'll be very easy to make it more efficient. There's so many places that could be like shaved off and made better. So every time we add one, we'd like to set instruction to instruction after setting instruction index to index. I think index plus plus is what I want. Okay, perfect. What happened? Too few arguments. There. Whoa. We no longer have to do that. Hey, look. We don't know what the adjacency matrix looks like, but we are supposedly creating it. So it's not a bad sign. Okay. So now we're going to have to iterate over this list twice. So we're going to have a list A, right? This will be instructions. I'm going to say while A. I mean, this could be a for loop again. For A equals A, next. How about that? How about that? So now, oh yeah, you ready for this? That's right. We replace A with B. So now we get every interaction between every instruction in this list. So we're going to loop through 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, etc. Then we're going to loop through 1, 0, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, etc. And then 2, 0, 2, 1, 2, 3, 2, 4. So we get literally every interaction. Right? And also 0, 0 and stuff like that, which is probably the first thing to protect against. If A, instruction, right? Yeah, if A equals B, we should just continue. Skip it. Right? But if, okay, if what? If adjacent. We don't have an adjacency matrix to tell us whether the two things are adjacent or not. So we're going to have to actually create the adjacent tester. Like is adjacent helper, basically. What makes things adjacent? I forget. I mean, I guess at this point, the only way we would know if two things are adjacent is with the actual thing. So I think it is adjum. Right? I think that's right. Okay, so if adjum of A and B, and remember we're now referring to them by index, so we have to use index. Then I have to give them a matrix too. So if we have already marked these as adjacent, that's basically what we're checking here. Don't check them again. And this is going to be G matrix. And then, okay, so if they're already adjacent, if they're equal, skip. And then I think at this point, we're going to have to do some fancy stuff to do with following control flows and everything. Are you ready? Are you ready? Okay. Basically, here it's going to be simple. We're basically going to say if, probably like, instructions interfere. Does that sound good? If instructions interfere, why did that not go well? And the instructions that interfere would be A instruction and B instruction. Then just go ahead and set in the matrix. That sounds so cool, set in the matrix. At these indices. Okay, so now we just have to define instructions interfere, which is like, this is the actual function that tells like the big daddy, do they actually interfere or not? So we're just going to return a char as a marker. We're going to be passed two instructions. We're just going to call them A and B still. Probably not the best, but not the worst. Okay, when do instructions interfere? I think I have this in my notes. Yeah, this is quite complicated. Okay, so basically, here's the just most basic top level note that I have. I'm pretty sure it's like an original quote from Surrey way back when. If the definition of B lies between definition of A and its use, then A and B interfere. Vice versa, if the definition of A lies between the definition of B and its use, then A and B interfere. So we have like this check. which has to be done both ways, on A and B, and also B and A. Here's the thing, we already loop over every single combination. So A and B will eventually swap. So I don't think we actually have to call it twice, right? So all we have to do is ensure that for every use of A, so it says that is more or less what I said. The direct quote would be two values interfere if either one is live at the definition point of the other. Lamau. Bless or aid. So yeah, basically for the uses of A, so for use pointer A use, which is equal to, whoops, which is, I'll get there, don't worry. While a use equals a use next. Okay? For every use of A, because here's the thing. What do we have? What is our little thing? If the definition of B lies between the definition of A and its use, then A and B interfere. And I think this would be said better. Any one of its... Oh, I get to piss off Sir Aid. That's so nice. And the definition of any one of its uses. No, I know. Shouldn't be there. Oh, that little single quote does make me happy. Sir Aid just put eyes in the chat. The emoji eyes. King Buns with a what is that? Feels amazing, man. Nice. That's the a progression of feels bad, man. Hilarious. So if a block, what is it called? Do we not have a block in here? Oh no. Oh no. We don't have upwards pointers. We really don't. Well, shouldn't be too hard to fix. In this insert function, I love that this is just not done. To do. Okay, cannot insert into a closed block. Okay, so there's no to do here. I mean, we just have to handle it, I guess, if we really wanted to. It's never happened. We never hit this assert, so we should be good. Okay. So we say add a new instruction, but we never actually keep track of new instruction block, which is surprising to me. It is the current block that we're inserting into, believe it or not. And guess what? We could also keep function, but I think this is fine. So now in error, instruction needs an IR block. And that should be good. It's kind of in the register allocation section. Okay. So now we keep track of the block. By default, return 0. They do not interfere. Okay, so if the block of A, because here's what we want to check. What we want to check is that the block of A is, if it's in, yeah. So if this use is in the same block as A is defined in. Right? I think that's right. I don't think that's too insane. Okay. So if A block, A use equals, no, if, okay, I can't speak. If the use of A and the definition of A, this specific use of A and this definition of A are in the same block, then all we have to ensure is that their indices are non-overlapping. That B's indices are non-overlapping. Does that make any sense? Because if B lies between the definition of A, so here we have the definition of A, which is just A, and then we have its use, right? And any one of its uses. This is one of its uses. So if it lies in the same block, then basically, if A index, is that right? Okay, we have to check if B is in the same block as well, right? Yeah, so if B isn't in the same block, then there's no way the definition of it could be between a use and a definition of another instruction that are in the same block. So B also must be in this block. I sound so insane, but I think this is correct. Right? I guess that could just be better said as A block at this point. So, Saraid says, you don't sound insane. That's good. This stuff is just insane, Lamal. Lol. You're right. So, if B is not in the same block, it can't... Okay, if definition of B is not in the same block, it can't be in between a use and definition of A that are in the same block. Sure. Okay, so if B block, A block, then all we have to check is that, so I don't really have to keep doing these tests. Pretty sure I could just say and. Well, okay. If definition and use of A are in the same block, and if definition of B, oops, Emacs is confusing like that. Okay, if definition of A and use of A are in the same block, and if definition of B is not in the same block, it can't be, okay, that doesn't make any sense, is also in the same block, the definition of B may be in between a use and definition of A that are in the same block. Okay, that is horrible. If definition of use of A are in the same block, and if the definition of B is also in the same block, it is a simple index comparison to check if interference, to check for interference. Okay. If a index is less than B index, because B would have to come after it, and B index is less than or equal to, so I guess a better way to say that would be to reverse it. So if the use of A index is greater than right? Yeah. Is greater than B index. What does this mean? Yeah. So if A, the use of A and the definition of B are all in the same block, if the indices of the index, I should say, of B is after the definition of A and before the definition of, or the use of A, that means it does lie in between, which means that it does interfere. Oh my God. Okay, let's not ever think about that again. Okay, so now there's an else. Right? There's always an else. A and B are not in the same block. Right? Are not defined in the same block. I guess this is why I did it the other way. Okay, we're gonna have to move this. We're gonna probably rewrite the comment, but it doesn't matter. See, the problem is we want to check that A and B are in the same block here, but we only want to check that A and A use are in the same block. See, I don't want to end up here where A and B are defined in the same block. Which I can if this fails. So if A and B are defined in the same block, but the use of A isn't in the same block, do I need this check at all? Hold on. Okay, so if the indices are within each other, that the only way this will work is if they're actually all in the same block. Otherwise, we can't guarantee that the indices are properly comparable because the instructions in a single block are meant to be in a row. So if they're not in a row, index would break everything. So basic blocks may be arranged in any way. That's why they jump to each other in that way. So these do all need to be the same. But only for this to happen, which means this probably should go like this. This may just be wrong. You know what? I'm just going to write it to do. Also, are you iterating over the blocks according to the control flow? Yeah, we're not there yet. We're getting there. To do. Are these ifs conditions in the right order? Slash correct. So we'll say, or even correct at all. That'll imbue the proper amount of confidence into whoever's reading it. Okay. This is where we're going to have to like follow control flow. I think we're literally just going to call it that. Follow control flow, right? And here's the thing. So we're going to need to like, do we need a callback? We need to, at each one of the blocks, we need to call a function. We'll try it. We're just going to try it for now. So we're going to say follow control flow, and we want to follow the A block, right? We want to reach user. Do I need B? Why would I need B? Is this correct? So effectively, when I follow the control flow, what are we going to do? This is horrible. Does it return anything? I don't know if it returns anything. It probably needs to return something, otherwise there's no reason to do it. Yeah, otherwise why would do it? So we're gonna have to like do an if. Okay, sure. Okay, so follow control flow. And it's probably going to return like a character or something, just a marker, something. And it looks like we're going to need an IR block. We're going to need a use, no, IR instruction user, and IR instruction B. We're going to give these better names. Return 0. Okay. So it says it has 3 different return values that all mean something different. Okay. So we should probably return like an int. Let's think about follow control flow. What is it going to have to do? Let me look at my notes as well. So follow control flow is basically going to what? What do my notes say? Okay, very helpful. My notes start with do not follow blocks we have already visited. Nice. Okay, so apparently we're going to be visiting blocks. Thread says you'd have to check my branch. There should be a comment explaining it, lol. That may be a good idea if I get stuck. That's definitely where we're going to be at. Yeah, that one's important, lol. Okie doke. So I think... Oh yeah, this is going to be rough. King Bun says overflows are fun. Oh yeah? What do we need to do? We need to have not just an instruction list. We need to have a block list. Because we need to store a list of blocks. There's so many better ways to do this, I know. I'm sorry. We could have a macro that defines the linked list at this point, and it would be used. So we have a linked IR block list. Okay, let's just start writing this one fucking right here. And basically what? So we're gonna have to keep track of all the blocks that we visit. So let's just add block to visited blocks list. That's probably another thing we're gonna have to have. Visited. Visited blocks. Okay. We're gonna say what? IR block list pointer new list entry, new entry, new block is equal to, I don't know, calc. I'm just gonna blast through this bad boy. Size of IR block list. Then we're gonna say visited. No, we're gonna say new block. Next equals block. No, equals visited. And then we can say new block. Block equals block. And then we can say visited equals new block. How about that? Okay, so we create a new block. We set its next to visited, the head. We update its data block, and then we set visited to new block. Looks pretty good to me. As you can tell, this is going to be a recursive function, at least at first. Okay, so we only want to add the block if we haven't visited it already. So visited iterator will equal visited. And then we'll say, I guess we can put this in a for loop. While visited iterator, is equal to visited iterator next. If our visited iterator contains a block that is equal to the block we are currently trying to follow, we can't follow that. So we're just going to return 0 or something. Does that make sense? Yeah, that makes sense. Yeah, so if we visited this block, just stop. You stop following. It means we're probably in a loop, and that's fine. Okay. Now, what do we do now? This isn't, obviously, we're not following control flow anywhere. So we add it to the linked list. Return 0 if block has been visited already. Okay. And basically, I mean, at this point, we just have to oh yeah, so we have to check like if they're interfering now, right? Am I wrong? My notes are so confusing. I have arrows going everywhere. So, oh God, what have I done? Yeah, okay, this is starting to make sense. So now I need to check so how do I check for interference here? Let me see if I have anything over here. I got nada. Okay, so it's going to be interference. Okay. Okay, here we go. Okay, so what do I have? If use and definition is in this block, and the definition precedes or is the same as the use, then the use and the definition interfere. What did I just say? If use and definition is in this block, that's incorrect, it's are in this block. If use and definition are in this block, and the definition precedes or is the same as the use, then the use and the definition interfere. So that's referring to the block we are given. And the use and be that we are given. So here, this thing. Okay. So this is the use of A. Zarias says, yeah, that for sure makes sense. I know. It's so confusing. Okay, so if use of A and definition of B, right? So this is, instead of calling this user, what would be more accurate, I'm a genius, would be a use. I think I'm gonna remove that. That's confusing. Use A. Yeah, we'll do A use snake case. It's fine. If use of A and definition of B are in this block, right? The block we are currently following, and the definition of B precedes, aka it comes before the use of A, then it stands to reason that B is in between A and its use, the definition of A, and its, once again, use, is B is in between the definition of A and its use, meaning there is an interference, is how I'll say it. How about that? And that's basically what we checked exactly down here, right? That's pretty much the same. I'm going to write it out so I don't get a copy-paste error. But basically, if a use block is equal to B block, what am I doing wrong? Okay, there we go. Is that right? Yeah, so if the use of A, they're in the same block, then we can just do an integer comparison. And we can say, okay, if, oh wait, is that the wrong block? Yeah, I don't care where the definition of B is. I just want to say if the use of A is in this block we are currently following. So if the use of A is in the block we're currently following, right, then basically we should also check that B, so if B definition is in this, yeah, okay, yeah. So the definition of B are in this block. So we need to say if A use equals block and B block equals block, right? So if both the use of A and the definition of B are in this block, and the definition of B precedes the use of A, if B, okay, so if B index is less than A use index, return, oh, so what do we have to return? We should probably make an enum control flow return value or whatever. Sure. So we're going to have something equal 0. What are the three cases? Okay, the B is that the cases are that we should continue following control flow. Control flow. So we're just going to do RA control flow. RA control flow. We're going to say interfere, right? We need to have a way to tell if they interfere or not. And then we're going to have RA control flow. And this is going to be cleared, which means that they don't interfere. Pretty sure returning 0 means we should just continue. We may want to change this behavior. Okay, then this means there's an interference, right? Boom. So they interfere. So in my notes, it says if B is copy, If B is copy, cannot interfere. If B is copy, cannot interfere. Okay. So at this point, then we can say B, is this right? And they cannot interfere. That just sounds really wrong to do. This sounds really wrong. Like, very wrong. If B type, right, is equal to IR copy, it just doesn't make any sense, man. Then it's clear. I think that makes some sense. Oh, but if they're not in the same block, then it's not cleared. This check has to kind of go here. Okay, we're doing ternary then. I may have made a mistake with the space button. We are good. So if it equals IR copy, then just return cleared. Otherwise, whoops, return interfere. So if it's not a copy, interfere, otherwise it's cleared. Okay. Does that make any sense? Why am I doing this check? I don't know, it's just in my notes. I feel like I'm just not gonna ignore it. I'm gonna leave it. So if B block, so I'm just skipping ahead a bit in my notes. B block is equal to block, then this means if only the definition of B is within block, then that means, okay, yeah. Then the use of A must come after. Right? If only the definition of B is within the block, then the use of A must come after. Otherwise, we would have seen it already. So that means that the definition of B is in between the definition of A and its use, which means we must return interfere, and I feel like it's going to be the same thing. And then I feel like here, I should return interfere, right? No, then that means they're cleared. But, oh yeah. So this is in the wrong spot, weirdly enough. So anytime we hit the A use block, we will return something. Anytime we hit the B block, that means that alone, and we haven't hit the A use block yet, that means that this exactly, the use of A must come after, so they must interfere. Again, unless it's a copy. I don't know why I have that in my notes, but I don't just write things for no reason. Does that make any sense? I don't even know at this point. Okay, then if they interfere, where were we? Yeah. So if this equals interfere, return an interference. What's the issue? Too few arguments to function call. Expected 4, have 3. What did I forget? Visited block list. Wait, do I even need to do this? Oh, I forgot. We're not done. I forgot something. My bad. It's fine. We'll get there. Okay. I don't think we actually followed the control flow, did we? I don't think so. Yeah, we didn't actually follow the control flow. That's a rip. So we called this callback, not this callback. We called this here, follow control flow, this function. It's supposed to be a recursive function. So this is what tells us whether or not they interfere. But if we are to continue, then we actually have to update some things. Do we not? Why would we ever return continue? What would that mean? Doesn't that just mean we should continue? So follow control flow, is it within a list, a loop? We're in here. So if follow control flow returns, let me just think about this. Yeah, okay. I don't think we need to return continue ever. I think continue can just be internal to here, because we would just be continuing by not returning. You know what I mean? We'll see what happens. We'll see what happens. Okay. So we would like to follow the control flow now. Actually follow control flow according to branch instruction, right? So we're going to basically switch. What was that? Yeah, give me that. Switch on the block branch type. By default, do nothing. But if it's return, I guess by default we should say like to do handle branch instruction type register allocation. What would it be? It's probably an integer. Do I need to put in a new line there? I don't think I do. We'll see. So if it's an IR, let's say return, right? We're at the end of a function. Then this means that we basically are done. So we can just return what do we return? I think we return interfere. Does this make any sense? So if we hit a return, we want to stop following control flow because we don't want to like move across functions, right? That sounds intense, and that's not what we want to do. So we're just going to call this continue, I guess. I don't think we actually need to continue. We don't need a break, but we'll put one to avoid warnings. What other branches do we have? We have an unconditional branch, which means that basically block is going to be equal to whatever the branch instruction is. pointing to? Block branch value block, right? And then that should be like continue. But what should that do when we continue? What should that be a part of? Basically, that just means we have to jump up to the beginning again here, right? Pretty sure. So this continue to do, we have to put everything in a bit of a loop. So continue then break. I know that'll never happen, but it's fine. Okay, here's the complicated one. Branch conditional. We have to follow 2 different control flows. And to do that, I mean, really, we just need to say probably enough to do our little fix. Perfect. Int result is equal to what? This is going to be the recursive call. So we're just going to pass in visited. We're going to pass in, I think, the next block. So this would be of the conditional branch. What did I just do? The conditional branch, which has a true branch. Okay, so we're going to go to the true branch. Then we have A use and B use. I think these are going to stay the same as A use and B, because we're still searching for the same thing. Okay, if result equal, basically if result does not equal continue, right? Is that right? Yeah. Return result. And then we can just go to the false branch by doing this first. Make that say false. Next, set block. Finally, continue. And this continue is basically just a way to get away with being recursive less. If we really wanted, we could get away with no recursion at all, but that would require a stack handler at the end here, which I don't, and then we have to create a custom register allocation control flow stack, and I'd rather just do this. Have it a little bit recursive, but do our best. And I'm pretty sure this is going to go in a loop. I mean, just loop forever until you don't. Okay. So forever, while one, return if block is visited already. Done. Add block to visited blocks list. Done. If use and definition of A and B are in this block and the definition of B precedes the use of A, then it stands to reason that B is in between the definition of A and its use, meaning there is an interference. Looks correct to me. If we run into the use of A, but B is not in the current block, that means we haven't run into it already. Do that down there, which means that they can't interfere, they are cleared. And then if B block equals block, this means we found the definition of B before the use of A, which means they do interfere. And then to follow the control flow, we handle these three instruction types. I think that's fine. Does that make any sense? Okay, Suraid says, basically, if A equals copy B, then A and B don't necessarily interfere just yet, because interfering means we don't want them to end up in the same register. But in this case, we actually would like them to end up in the same register. This does not apply if A and B are both pre-colored, though. So what you're saying is to each one of these copies, I should add and... Oh, that didn't work. I should add like and... What would I end it with? I basically want to check that, what? What'd you say? If A and B are both pre-colored. So we only want to clear them if it's a copy, and so if B is a copy, and A and B are not pre-colored. How do we know that? I mean, we don't even have A at this point. I'm not even going to worry about it. We're going to call it good. Could add a little to-do. To-do. Check that A and B are not pre-colored before clearing. Looks good to me. Okay, so if instructions interfere, follow control flow. We need visited now. So this is null. Is that okay? This will just not run. Yeah, we never dereference visited. Not once. We do the visited iterator, but only if it's non-null. Very cool. So if they interfere, they interfere. Holy crap. So is that done? Is that right? Now we have to have a way to print the adjacency matrix, right? Let's do that. I'm gonna have to use a restroom too. Okay. We're basically just gonna need the graph. We'll just give me the matrix itself. We'll call it M. Okay, so for size t y, y is less than what? M dot size plus y. Okay, copy that. Sadly, there's foff in it. Replace with x. We're basically going to want to print out a 1-byte integer. How do I do that? Well, I don't want to print, so it'd be, what is it? I don't remember, honestly. I don't remember. How to print 1 byte. We'll get there. And this is going to be whether something is adjacent in the adjacency matrix at x and y. Okay. So we're going to do something like this. And handle the first one like a sensible person. So we can print a new line. We can print, hopefully, I really just got to look it up. Print out, format. Oh man, okay. Which was promoted from a char, which was promoted from a short. What does that even mean? So it looks like HH is the way to go. UHH, is that correct? Is it HHD? That's probably what it is, HHD. Which means if we want unsigned, then yeah, that's how that'd go. Oh boy. Uh-oh. Uh-oh, chat. Exited abnormally. Which part do you think it was? Think it was anything here? No, we never call print adjacency matrix. So if we never call instructions interfere, it works. What if we call instructions interfere but never call adjacency set? Okay, we still get an issue. So we know that it's in instructions interfere. So for every use of A, I guess should we check for null? These really shouldn't be null. My Lisp is coming out. If not A or not B, turn 0. I mean, we don't want it to be past null, but if it is, we want it to protect against it. Okay. We could even do like an assert there or something instead. So, to do assert instead. Okay. So then we have a use, which goes until it's null, which equals a use next, which equals a uses. Everything's fine there. So if user is null, that would be a problem. If a use user this stuff is like a horrible headache. Yeah, it's not too bad. Panic here. Okay. A and B are valid. I hope. Probably just assert A and B. Cannot get interference of null instructions. Hey. Zaria says, hopefully you start a new thing soon. I just joined yesterday and have no idea what's happening, to be honest. If you have any questions, let me know. I'm here to help. Sarade says, I'd help, but I'm currently parsing POSIX shell commands, and that's already enough of a headache for me. And also, I've spent way too much time looking at my version of values interfere. Well, it is all good. Don't worry about it. I will definitely track it down. So we follow the control flow. So this null pointer is an immediate red flag. visited. Does visited run, like does a for loop run if the condition fails? It does check the condition first, right? Even on the first iteration it says, if visited it, do this. We're not just dereferencing null right here. Sarade says it checks it first. It doesn't run if the condition is false. Okay, so we don't have to do that. I'm going to trust Sarade on that one. King Bun says, yeah, we'll check. All right. Zarya says, well, I am not sure what do I understand, so I'm just reading code to try to understand the code base. Nice. There's a developer PDF, which looks like this. It is not up to date, but it is the best thing we have so far if you want to get an overall idea of what this is like. To see this PDF, it's in the docs file. Just go the docs folder, and then it's under developers.tech. And then in developers.tech, you just have to compile it using some sort of LaTeX engine, preferably ZTech or something like that, XETEX. And then you'll be able to see the PDF and read it in all of its glory, hopefully gaining some understanding of the underlying structure of the compiler, because that's exactly what that is for. Where's the repo at, bud? It's it's at the GitHub, or in the it's at the GitHub down below. Sarade says exe latex actually. Yeah, that's true. That's the engine. ZTeX is like the flavor. Exe latex is what it's called, lol. Is it really? I've heard it called ZTech all the time. King Buns with the link to Fun Compiler. What a pog. Thank you, King Buns. I appreciate it. On behalf. Okay, so what is going wrong? So when we continue, block is updated. So this visited list lives, I mean, it just gets created. So it doesn't even need to be, I mean, it gets created at the top level. So visited it equals visited, if visited it. Okay. So we're not doing a null dereference here. Calix size of IR block list into new block next visited, new block visited new block. That's not insane. So it's got to be somewhere here. What's going on? So maybe return is returning the wrong thing. So return should basically mean that we're done searching. No? Okay, no, that wasn't it, at least. That may be true. Sarade says, I think ZTech is the underlying engine or something. I think you have it backwards, Sarade. I think ZLaTeX is like the name of it, or the underlying engine, excuse me, and then ZTech is the actual, like, the name of it. I don't know, though. I could be wrong. I often am. Okay, we're gonna go here. Boo-doo-doo, boop, boop. I will show you where I'm going in just a moment. No, but the thing is, LaTeX is based on tech, not the other way around. What? Yes. So it would be logical if zLatex is based on / uses ztech. Yeah, I don't think that's how that works at all. I'm pretty sure they're just the same thing. I could be wrong, but I'm pretty sure ztech and zLatex are the same thing. Maybe I'm wrong. One of them is like the underlying engine, one of them's like the marketing name. Could be wrong though. We are what? We're gonna look at register allocation. Welcome to Sir Aid's branch. We're gonna copy from him. Okay, values interfere callback. I don't know why it was done this way. I'm sure there was a reason. So we pass through parent, the callback, use parent, and v2. What does that even mean? What is v1? Block. Use of v1, definition of v2. So this is our A use and B. The use is in this block. Hey, look. The parent of a value is a block. The parent of a use is a value. Oh, yeah, that's sensible. I like it. Sraid says ztech is a typesetting engine. zLatex is a format file for compiling LaTeX formatted documents with the ztech engine. Okay, so ztech is the engine. You are correct, right? ztech is the engine, but then zLatex is actually the format. Okay. Why? So move on to the next block. When would we move on to the next block? Values interfere callback. That's when we call the callback in follow control flow. Where's follow control flow? Okay, at the very top. Why was it done this way? I don't know. Because is there a variable amount of arguments? There's a big comment at the top of values interfere. I hope it explains everything. I don't think it will. Yep, this iterates over each use in v1 and checks if the definition of v2. Follow control flow is supposed to be generic. Why? When the IR isn't generic. The IR is the IR, there's only certain instructions. You're saying whether things interfere or not? I don't even know. I don't know what that means. I'm not going to think about it. This iterates over each use in v1 and checks if the definition of v2 lies within the interval between the definition of v1 and the use. That's exactly what we do. Okay. If the definition of v2 is contained within any of these intervals, v1 and v2 interfere. If so, return 1, 0 otherwise. So when we call values interfere, Saraid says, I don't know, I thought I'd need it somewhere else again, lol. That's fair. That's fair. So for every use of A, if A, what? So if the definition and the use of A are in the same block, the definition of v2 is also in that block and lies between the definition of v1 and its use, then v1 and v2 interfere. So that refers to here, right? Whoop. Okay. Follow control flow. Basically, return if block has been visited already. So this didn't work. where's follow control flow? And how's it different from values interfere? Why does values interfere call follow control flow? So that is effectively my okay, instructions interfere. Okay, I'm starting to get it now. V2 parent equals V1 parent. So if A and B are in the same block, if A and B are in the same block, if the use of A and A are in the same block, right, as well, so no matter what we return here, maybe that's what I'm doing wrong. Because we can fall through here when we shouldn't, maybe. So we return A and B are in the same block, and then the index checks. Maybe that's the way to go. Return A and B, whoops, in the same block. I don't know how this would be breaking things, how it was, but I'm not even going to think about that at the moment. Okay. Yes. Else, they're in different blocks. That doesn't really track, but okay. So if V1 parent, so if A block equals use of A block, return that thing. Okay, no, it didn't work. Exited with code 5. Just make sure. So A use has to be valid, but A use user doesn't. So let's just assert A use user. Use instruction cannot be null. Okay. Anything else we dereference? We dereference A and B. We dereference A use all the time, but that's never null. So it's not a dereference here. It's not memory here. Fun. So when we're looping over this, if this, else, follow control flow on the block that you're currently in. What does that mean? Yeah, so A block, that's what that means. Values interfere callback, that's generic stuff. Use parent and V2. Use parent and V2. So use parent sounds like the block, but that's actually the instruction B. And this is the user instruction. Yeah, user and B. That makes sense. And then if it equals 1, return 1. So when does follow control flow return 1? Of course, it's up here. Sensible. Of course, it's variadic. Sensible. Okay, use parent is the value. Yes, again, the naming is confusing. It's all good. So we have block. What is control flow iteration context? Why is that needed? Where is that even defined? What? What have you done? Is it right in front of my eyes? When do we ever interact with it? Saraid says you're missing it. Just Control F for it. That means I'm not just missing it. That means it's just not on screen. Okay, so control flow iteration context. It's a vector of basic blocks. Okay. So that's your way of saying visited blocks. Whatever. Basic block, current block. So we have visited blocks. We have the block. We have the use and B, which you made variadic. We already visited this block, return 0. That tracks. Otherwise, add this block to the visited blocks. It's variadic, so you can pass multiple values to the callback. I see. Interestingness. Not saying that's the best way of doing it. It's a little interesting. So you call the callback, and then if result, return result. So the callback, this is so easy to understand, is the values interfere callback, which of course is variadic. So we have a use and a def, a use, so this is A use and B, hence. So this starts our callback here, basically. The use is in this block. The def is in this block and proceeds or is the same as the use, then the use and def interfere. Okay, so what am I doing here? A use, B. These are things that have been asserted? No? Probably not. A use cannot follow control flow of null use. Cannot follow control flow of null instruction. I guess this would be definition, to be more accurate or succinct. Okay, still doesn't work. So it's none of these issues here. Okay. I'm really hoping it's one of these things. I mean, I'm not, because that would mean it's kind of a huge issue. So block is null. Huh. Who would have thought that a block is null? Which instruction is that? Okay. If not a block, then what? Probably a copy you're inserting. Saraid, you are onto something. Let's just do this anyway. It's not going to hurt us. Rip. It's the first one. It's the first one. So when we insert an instruction, we call into IR blah, 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 right? So when we call IR_insert, which is what happens when the insert thing happens, the macro, then we ensure that the new instruction has its block set to context block. So if we panic with here, we did not panic with here. So context block is being set properly here. What? How does that work? My version of IR_insert is like 20 to 30 lines of code because there's too many corner cases. So it says, are you ever setting the parent? Yeah, right here in IR_insert. Lamau. So we have the block. So every time we call insert, for example, for a global address, you'd think that its block would be set. What in the world, dog? So context block. Okay, what if this happens? We should probably do this then. Fuck. Okay, now you're right. Now you're right, Saraid. Now it is the actual insert blah. Right? And we're basically inserting A into the block of B. So we're going to say A block is equal to B block. And same here. Hey, poggers. Poggers, poggers. It's working once more. Wait, does that mean... That means we're getting quite far through, then. It is. We now get to see how ugly this is. What just happened? Okay, let's see how ugly it is. Okay, it didn't print anything out. What happened? Why didn't we print anything out? Come on. So we build the adjacency matrix. When we print the adjacency matrix, is matrix.size 0 somehow? Build adjacency matrix. We say adjm create. Which says size equals size. Which is instructions, instruction index. I see. That's not the size of the list, because we're starting at the 0th index, obviously. So we don't actually have a helper to add to it or anything. So we're just gonna do this by hand. Lamau. Basically, we just need the last instructions. Okay. While last next. Last equals last next. Not ideal. Also broken. Fuck, man. What did I just do? Is it here? No. It's got to be here then? Okay. We're going to assert instructions. Oh, man. Cannot build adjacency matrix of null instruction list. That sounds sensible. Okay, it doesn't trigger. This is so interesting. Why? Why is it not working? Okay. I just had my keyboard act a little odd, that's all. So size is equal to this thing. But right now, size is going to be equal to fucking, I don't know. I don't know how to get the size. So it's going to be 0. Right? That works. If it's 1, does it work? It works if it's 1. 10. 10 breaks. Now that's a confusing one. So what if I just did that? Okay, so it's not happening there. Somehow accessing memory that we shouldn't for the adjacency matrix. They all just use this one. Y times size plus x. Oh, that would be an issue, yeah. It's two-dimensional. Oh, man. Okay, it still didn't work. Still didn't work, okay. So our adjacency matrix is two-dimensional, obviously, so we definitely fixed that a little bit. So when we access it, if we imagine that the size is 10, as we are, then that means that we could have a y of up to 9. So 9 times 10 would be 90, plus 9. That'd be 99, and if it's 10 by 10, that would be within. So that'd be the very last value, right? So this seems to make sense. This does seem to make sense. I mean, adjm set and clear are fairly understandable. This gets the address of data at blah. We could also just do this. I don't think that'll help. What could it be? Might it be time to break out a stupid debugger? It may. So we're going to say if x is greater than size, x just return m.data 0. I think that makes sense. Okay, that seems like it was it. Oh, wow. Hello. Okay. So why was it too large? Probably because size is being hard-coded. Why did it work when it was smaller? See, that's also confusing. Okay. I think I fixed whatever the issue was. I don't really know what it was. Here's our adjacency matrix between all of our instructions in this list. Okay, so we're going to steal this, place it here. We are going to, on each row, print out the y, I guess is what it would be. Something like that. Yeah. And then do the HHU thing. Okay. And then at the beginning, I would like to say one of these. And start at 0, please. And for every row, first of all, we're going to want to print out something as an equal size to this, which we can't because it's a format. So an equal size to this at the beginning, I think should be fine. And then I can just add like something like this. Okay, I know this is horrible printfing, but it's fine. So what would I like to do? Make it 4, and then thing, pipe, space, and then I want to label the first one, right? So the label is going to be 0 because this is the first one. So it doesn't need to be a size t. And then on subsequent ones, it should just be x. So this does still start at 1. And then we print x like that. Does this work? Okay, that did work somewhat. I don't think I added a new line. It's going to break things. I saw it in there. So the comma adds an extra space. Other than that, other than the comma adding 2 spaces instead of 1. Okay. It gets there until the double digits. So what we should be doing is putting each one in the same, like this, 1 space and then 3. Just do 4. What does that look like? It's probably way too large, right? Yeah, way too spaced out. So if we did like 2, then each of these HHU, we could also put a 2 in front of? No? This is some heavy format stringing. If you can manage to fit the whole thing on the screen. Okay, it's still not correct. Damn it. Now I think I just need that extra space to handle the comma. It's nearly there. It's one off. Okay. That is at least better. Okay. That should be it. That is a matrix and a half, ain't it? I guess we could just do without the commas as well. In which case, boink, boink, boink. What do we got? Yeah, that's better. Now it's one off again. Okay, so we needed that second space no matter what. Good to know. Here we go. We've done it. It was rough, but we've done it. As you can see, most of this is unused, but there are key things that are not. For example, 16 interferes with 17, which also means that 17 should interfere with 16, right? Like vice versa. So 16, 17 means that we should also have 17, 16, which is true. But so should we also have 16, 17 then? Do we need it? Does it matter? So this problem has to do with our indices. So when we call adjacency set, or entry, let's say, what is it, adjm? Okay, so we know if x is greater than blah, do blah. But if x is greater than y, here, it really doesn't matter which way we do this, I don't think. If y is greater than x, then x needs to equal y needs to equal old x. And old x can be on the stack. Okay. So now, whenever we get an entry, we should always get the same one. So if we set 8 and 7, or 7 and 8, it shouldn't matter, we should get the same one. And you can see that here, how it's reflected in the symmetrical table on the center line. So technically, when we print out this thing, we should technically say x is less than x, right? Does that even make sense? So here's the thing. We only want to print as many columns as there are rows so far. So in our x, we only want to print out the columns for x is less than y. There you go. Ain't that a beaut? Okay, so this is our adjacency matrix. I guess we could also have x start at y and then make the upper half, but either way, it doesn't matter. I kind of then want to print this at the bottom. Is that doable? I know I'm spending way too much time on something that doesn't matter, but what are you going to do about it? Okay. That's it. It's incorrect again. No, it's not. It's fine. It's correct. So I'm wondering if each one should have no spaces, but actually be three or four or something like that. I think either way it's going to be off. Okay, I don't matter. It doesn't matter to me then. And oh. Okay. I don't really want to keep track of the width. This is complicated enough already. It's fine. This is good. Update. I can now run my shell from within my shell. Oh, pog. That's actually exciting. So we have our interference matrix. Hallelujah. How about that? It looks correct as well, which is a good sign. So now that we have this adjacency matrix, it gets more complicated. Did you know that? Bet you could have guessed. So we now need to coalesce registers. That's right. And then basically do everything again. Yeah. So we collect our instructions, build the adjacency matrix. Then what we're going to do is coalesce, right? And then we're basically going to do this again. But I'm pretty sure instructions will be different. Okay. Let's think about, okay, I am, right, it says lower triangular matrix, nice. Yeah, I figured by adding adjum entry, just by adding this if y is greater than x, then it means that we'll never have to set like x and y and x because these are bidirectional edges, so we want both to be connected. So when you check an x and a y, if they're flipped, it doesn't actually matter. It'll access the same memory. There's probably some crazy stuff I could do and allocate less memory and have some crazy indexing, but this is fine for now. You could even just move it to a bit field and it'd be better. Serade says, that's pretty much what I did, lol. Awesome. That's perfect then. Because yours works. Okay, so we now need to coalesce. What does that even mean, right? What is coalesce? So I'm pretty sure it means to like bring together. Also, does coalesce have two L's? Am I wrong? Coalesce. Okay. 1 L. Saraid says, except my version has like 100-line comment explaining how index calculations work, lol, because my adjacency matrix also contains the registers. Oh, Christ. Why would you do that? Why would you do that to yourself? Okay. We're probably going to need this. We almost always need this. So coalescing, what I have in my thing is we keep an IR instruction list. Instructions to remove. Right? Which is going to equal null. Sorry, it says because values can interfere with registers. Yes, but also you don't need to include them in the adjacency matrix for that to be a thing, as far as I'm concerned. So we're going to keep a list of instructions to remove. To do, remove instructions. We're going to keep a pointer to an IR instruction list. Instructions. And then we'll take in our graph G. Adjacency graph, is that what I called it? And a pointer as well. The adjacency matrix is temporary anyway. Once we get to adjacency lists, the interfering registers are stored as a bit mask. Exactly, in my implementation, that is. It won't be different in mine. Well, it may be. We may just use an array of bytes instead of a bit mask. Who knows? So while instructions to remove, we'll just do it. Then we'll say, what? Basically, oh man, this is going to be complicated. We're going to have to like delete from block. Delete instruction from block. That's going to be a whole thing. And then this can actually be a for. Equals. Oops. Okay. To do. Delete instruction from block. Big to do. King Bun says, I somehow ended up on your GitHub. I love the how to do things repo at Saraid. Legendary. Oh yeah. Okay, so in between here, we have to decide which instructions are removable. So attempt to remove copy instructions. Basically a copy, if you can get away with it, you can just store in the same register and not actually ever have to copy. So let's do that. So we're going to make an iterator, which is going to equal instructions. This is probably going to need to be a pointer. While iterator equals iterator next. Hey. Saraid says Lamau. Yeah, that one's pretty useful, haha. King Bun says function download what, Lamau? Is that from the how to do things? So this is an it instruction. So we can just get our instruction out of it right away. Say this equals it instruction. Okay. If it's a copy, okay, if it's a copy, so if it's a copy of itself, we can definitely copy it. I have that in my notes, if it's a copy of itself. So if instruction is equal to the thing being copied, which is value reference, then we can just say, hey, you're good. Wait, what do we actually have to do? So if instruction equals reference, well, then we have to make sure that they're stored in the same place. For example, if pre-allocations happen, if instruction result equals copy so if they are stored in the same register, then replace all uses of instruction with copy instruction, with thing being copied. Okay. That would make sense. And then we should just say add to instructions to remove. So instructions to remove equals a new instruction, basically. So we're going to have to do here's what we'll do. So instructions to remove. So create a new head. Set head instruction to instruction, the copy instruction that we'd like to remove. And then replace the head of the linked list. Okay, and then we can continue to the next instruction. It's been handled. Okay. So if instruction equals reference, I guess, or if the instruction result is set, so if, yeah, basically, or if the instruction, so if the instruction has already been allocated a register for some reason, then that will be set, which means that, here, this is going to need to be in parens. So if instruction result and instruction result equals instruction value reference result. So maybe I can just say if instruction result and let the next thing handle it. Because if this is false, yeah. So or instruction result, or if not adjacent in the matrix, that sounds so cool, of G matrix, and then this would be the indices, right? So this would be not A, but instruction and instruction value reference index. So if the copy has a pre-allocated register, if the copy is equal to itself, it's a copy of itself. Or if the copy and itself are not adjacent, that means you can just store them in the same register, given that they haven't been assigned previously. Okay. So where does this go? So if these aren't true, do I even need to do that? I think I do. So this if will continue if this happens. This else will continue no matter what. But this if will fall through if this if fails, which means we will end up here. And this means that the copy instruction has a result, but the instruction that's being copied doesn't. Instruction has result, but so instruction result, right? Then if okay, so if there's already a result set, this is what we're going to check for. So value reference result. Continue. Don't override anything that is already colored. So the result refers to the graph coloring, aka the register allocation. So if there's already a result register, don't touch it. But if there isn't one, we can then say this is equal to instruction result. If none of them, if instruction result is 0, well, then that means we can just remove the copy. Why is it even there? Okay. So remove copy again. So this is going to be this thing, literally just exactly, right? Replace all uses of instruction with thing being copied. Head instruction, head next, instructions to remove head. I think that'll do her. Okay. So this is if it's a copy. No, that's the for loop. This is if it's a copy. No. Well, that's not supposed to end there. Lol. It's supposed to end like there. If it's a copy. Okay. So we'll fall through to here. This control flow is something else, ain't it? Yeah. So after we do that, I mean, then what? Then we just fall through, right? We fall through from both of these. Okay, so then here's the thing. Also replace all, this is what's in my notes. Also replace all adjacency matrix values. Replace in what way? Regarding, so it makes sense that because we're getting rid of an instruction, that the adjacency matrix should be updated, otherwise this adjum thing is going to really, really not like you. So to replace all adjacency matrix values, what does this mean? So this means that the adjacency entry for the copy instruction should actually equal the adjacency entry of the copied instruction. So replace all adjacency matrix values regarding copy instruction with the copied instruction. Okay, so we're going to just loop over the list, and this will just be our adjacency iterator. Why not? And we'll call it instructions, our pointer. So now for, I guess I'll move this here. Adjacency iterator equals next. Okay. And basically, instruction, so if the one we're doing we want to skip the instruction, the copy instruction itself. I guess we don't even really need to do this, but it doesn't matter. So then we just basically need to say that the adjacency entry in the matrix at the copy instruction nope, I did that wrong. So the copy instruction should be the same as does this even make sense? I don't think my notes make any sense here. It wants me to do this, I'm pretty sure. Or I'm just reading what I'm remembering wrong. It like, so we're supposed to copy this over. So the entry referring to the copied instruction is copied into here at the copy instruction. To do delete instruction from block. Let's do that so we can actually see what this looks like. Nothing on that. Okay, rip. So delete instruction from block. What does that actually mean? Basically, if, okay, so we're gonna have to get our instruction. So we're gonna say our instruction equals instructions to remove instruction. if instruction, hold up. Hey. I don't think that's what I want to do. If instruction previous. Then we want to dereference it and set its next to instruction next. If instruction next, then next previous should be set to previous. Basically removing from the linked list. If instruction is equal to the last instruction in the block, then we're going to say the last instruction in the block is now instruction previous. Does that make sense? I think that makes sense. Oh, I forgot to check as well if instruction equals instruction block instructions, then that means it's the first one, which means that instruction block instructions should actually be set to instruction next. Okay. Okay. To do is like free uses. And then we can just set everything to null so that we don't fuck it up. We'll just make it all null. Okay. That would be that. So we remove this instruction from the block. Cool. That should work. Now we just have to go through and everywhere we say replace uses, we should probably go and do that. First, I'm going to use the restroom really fast. I will be right back. I made it. I'm back. Hopefully none of y'all left. Okay, where were we? Basically, we have to replace all uses of instruction with the thing being copied. Okay, so we should probably make this a function. Replace uses. What's it going to require? King Buns says I left. Oh no. Lamau. That was good. I'm screwing everything up. So basically, we're going to have a thing being used, right? We're going to have the actual use that we'd like to replace, and then we're going to have its replacement. That makes sense. That makes sense to me, right? So basically, if our use replacement already refers to the replacement, then we don't have to do anything. So what are we doing here? Basically, we want to switch on the user type, right? Switching on the user type. Because what this will do is so any pointer within value is what we have to update. So for example, anything within here that refers to an IR instruction may refer to the thing being used, so it may have to be replaced. So I think the easiest way to do that, like I said, is with switching on the type. And then we can just look at intermediate representation.c and see like return. And you can see that when we create an IR return thing, that it doesn't contain any IR instructions. I think that's doable. So case IR return, it's nothing to do, right? That's what I would say. So this is just going to be break. Default to do handle IR instruction type to be able to replace uses. I mean, that's a horrible error, but it's good enough. Okay. So case IR, what else wouldn't really do much? I mean, I guess I could just see, yeah, we'll just do this. So here's femit, set IDs, add function call, phi argument phi. Okay. So if I see an instruction, IR instruction parameter, then that means I need to possibly replace it. So for IR load, then that means that we are going to have to look at the reference right, value reference, and if it equals uz, we would like to replace uz with replacement. I don't think that's too insane. Hopefully not, at least. What does IR load even do? Is it even used? I don't know. In any case, if this equals uz, update it to replacement. This is kind of the pattern we're going to be following for a while. Direct call, indirect call. Okay, so we're gonna do something like this. Sorate says, I'm getting a network error message, or is that just me? Hopefully it's just you. Everything's good on my end. Let me check Twitch itself. I was able to load my own stream. So everything is good on my end. I can load through Twitch. Everything's good. And will that really help? Sorry, it says weird. RIP. Reloading doesn't help either. I'm able to load in Twitch. If use user value call type equals IR call type indirect, if callee equals usee, callee replacement. Load local address. Which just uses reference. So local address. Local load. Sorate says, nope, it just doesn't load for me. Anyone else experiencing this? I'm assuming no. No one answered. Sorate says, huh, it's not just your stream. Weird. I wonder if Twitch is bugging for you. Store global. So we're going to have to handle that. And then that's global assignment new value. If that equals UZ, that equals replacement. Store local uses the pair. Sorry, it says, oh, okay, it's back now, never mind. Lit. Sorry, it says, I saw like 2 frames or so. RIP. Okay, it's back now, never mind. Okay. It's not back. You saw 2 frames though, you're getting something. And now it's gone again. Oh, that's so good. Hire local store. So we need to check car encoder of pair. Hey. Oops. That was crazy. And then and cdr. Okay. We have store, which is just a big to-do. I assume with data and address, store would be a pair as well. And we don't even have a thing. Okay, branch conditional. We got a whole bunch of stuff to check. Okay. Gonna check this. Okay. We got some stuff in the Discord. What do we got? Toaster. Hello everyone, Master Code here. Just wanted to say, Lander says Lua is the best language. What a troll. Beetlejuice says, you are self-taught? Wow, I am also self-taught, but I am not a systems programmer and not working professionally. I'm hoping to build a career out of this. I've learned that Andreas was also a self-taught programmer the other day. Seems there are many self-taught systems programmers. It's true. There's not really a good way to learn it in school, at least for me. Mr. Mugume with the response to King Buns. I figured you needed to smile since you were playing Valorant, and no one smiles playing Valorant. Lamau. And then Sarade with the network error. Error 2000. RIP. Apparently it's not just me. Other people are also getting errors. They are? They are? No, hopefully it's fine. Sarade says, it seems that Twitch is currently less than operational. It's okay. We don't need Twitch. So we just need to check the condition in branch conditional. Okay. Branch. Copy has reference. King Bun says, has been stable for me so far. Crazy. It's probably something localized to one of their CDNs. Comparison has a left and a right-hand side of pair. So wherever we did pair, add comparison. King Bun says West Coast gang. That's an actual gang. IR add also pair. Same with subtract. Case IR subtract. We have multiply, divide, modulo as well, which we should probably do. Shift left, shift right, stack allocate. Those are important. Those are important. But they're all just going to end up here. So, not too bad. And, okay, so now we can assert that IR instruction IR count is equal to whatever it currently is. It's 18. So hopefully we've handled them all here. We have IR phi, which For IR do we have to like follow arguments and stuff? How far do we have to do a replacement? We should probably follow phi arguments, so let's do that. So we're gonna say basically for every argument, we are going to call that user value phi argument, while phi equals phi next. Okay, then we can just say if phi value equals uz, phi value equals replacement. I think that's sensible. Okay, so local address, local load, and IR copy. We have branch, return. So let's just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 out of 18. What are we missing? IR immediate. That would be 1. Okay, so there's IR immediate. What about IR load? I'm pretty sure we already handled that. Call, handled call. Load global address. So when we load an address, there's no thing to actually replace. So global load. Local address, there's something to replace. Global load. What did I just pass up here? Load global address. Oh, okay. So in both of these, no use replacement needed. Global address, nothing. Local address, yes. Global, no. Local, yes. Store global, yes. Store local, yes. Store, yes. Branch conditional, yes. Branch, return, copy, comparison, add, subtract, blah, blah, blah. All the rest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm missing 1. Parameter reference. When do I create a parameter reference? Parameter reference just has an immediate, so we can just say we don't need to deal with that here. That'd be the one. Okay, now we should handle them all. Fantastic. So now we just need to actually replace all uses. So this is actually not replace uses. This is replace use, right? So let's replace all uses by doing something like having a simple wrapper. Replace uses can basically just take in all the same things. Of course, we don't need the uses, each individual one. Then we can just loop over the uses. Use equals use uses. use. So maybe this would be better as instruction. Okay, use equals use next. Okay. Then we can just call replace use in here on instruction with this use, and this is the replacement. There we go. Replace uses of instruction with the thing being copied. Is that right? I think that's right. And then we're just going to do the same thing down here, right? Okay. And that should be right. Moment of truth. Called it with the wrong number of arguments. That's fine. Hey, that's Pog. Well, it worked. King Buns with the Pepe. Who is that? Feels good, man. Man, I don't even recognize Feels good, man. What's wrong with me? My internet culture is defeated. So as you can see, nothing changed. King Bun says amateur hour. Lamau. So there's still 36 here. But as you can see, we're starting to assign registers. As you can see, which is good. That's very good. Okay, which means we're able to get rid of as many copies as possible. Amateur Hour says it's getting there. Amateur Hour says, King Bun says it's getting there. Can't read, man. Okay. King Bun's Lamau, Amateur Hour says. It just slipped out, you know? Okay, what do we do after coalescing? We basically just color the graph. Okay. So it's dark in here, but I'm pretty sure. Yeah, I basically just have to build the stack. Ooh. I'm just gonna get this done today out of sheer anger. Ugh, I keep getting voting texts, but they're not even to me. It's like, hey, we heard you live in Arizona. It's like, sure do. Oh. Okay, so King Bun says, I get daily mail. Jesus. Seriously? At that point, it's just annoying. Okay. There's one thing left to do, actually. And this is to, after we've coalesced, and rebuilt, we need to actually build our adjacency lists. Okay, so an adjacency list is what we're going to be dealing with the most too. Where are these? First time chat from Stunner99. Greetings, like an alien. How much time you needed to get your first job as self-taught programmer? I would be wondering the same thing. If I wanted a job as one, I'm sure I could get it. I just don't want one. But that's going to be different based on your opportunities, where you are, what kind of person you are, your personality, are you good in interviews, stuff like that. It's going to be, I can't really answer that for you. Because for me, it's not applicable. Okay, so we're going to need to build adjacency lists. We're going to need to feed it G, info, and instructions, I'm sure. Okay. Yes, it goes further. So an adjacency list adjacency matrix okay. Begin adjacency lists. End adjacency lists. Perfect. Thank you so much, King Buns. You know, sometimes people are just waiting for you to say what you want them to hear. They don't really care what you have to say. It's like when someone asks you for advice and then you tell them to do something, they do the opposite. It's like, why'd you ask? You didn't actually care. It's fine, it's fine. So we're basically gonna have a singly linked list. We're gonna have a color, a degree. So degree refers to how many adjacencies this vertex / node has. Neighbor count is how you can think of that. I'm going to have an adjacency list pointer. Adjacencies. Oh, but this... Okay, we're going to have to do this a little differently. So we're going to have an adjacency list, which has like a node and a next. Perfect. Serade says, all right, I turned on my VPN, but it's still buffering. Twitch is dying at the moment, it seems. RIP. King Puns, have you tried turning it off and on again? That's a good question. It's honestly a good question. Have you? do a little bit of a forward declare. Okay. So now, with our list of adjacencies, this will be like its own list that stores any amount of adjacencies, degree amount of adjacencies, actually. So then we can have the instruction that this refers to. We can have, for some reason in my notes it says each one should be uniquely indexed. So I'm just going to say index, let's say unique integer index. We have an allocated flag, and then other flags as well for spilling. Why did I do that? Okay. Okie doke. Thread says I have multiple times. Oh, rip. So sorry, Sarade. You shouldn't have to deal with stuff like this. Okay. Now we're just going to create our basic API. So we're going to do Agile this time, which is why we used Agim before. And what is create going to do, actually? It's basically going to return list after creating an adjacency list, pointer list, calloc 1, size of list, adjacency list. Okay. List. Here, we should probably take in info. And then we can say head. Is that needed? Why would we need info? Again, things in the notes that don't always make sense. I love how they're just super detailed in some places, and other times it's like, I don't know, good luck. We just need the head to add to, right? And we're going to say create this new list, which is also going to need a new node as part of it. Okay. And then basically we want to say list next equals head. And then list node equals node. Okay. So we create a new list, create a new node. Update the node. That kind of seems okay. So it says, also, in case you want to ask me something about my IR branch, do it on Discord, because at the moment I can just barely make out half of what you're saying because of constant buffering. Thank you, thank you. Had to respond in chat, make sure he gets it. So we should probably add an adjacency, right? I suck at naming things. Yeah, this will add a new list, a new adjacency, basically. Okay. So what we're going to need to do is, we're probably going to need an adjacency list node, an adjacency list node, adjacents. Okay. We then need to add Agile create, right? But this is actually going to be on node adjacencies. So this will equal new adjacencies. So then we can just say node adjacencies node equals adjacent. Oh boy, I think that makes sense. So we create, one thing we have to do because of this pattern, be sure to assign return value. Assign given head to return value. Okay, so we do node adjacencies equals Agile create node adjacencies. We basically just create a new head and assign it. I guess we could say head equals if we did something like this. List next equals head, and then we'd have, that seems overcomplicated. This is easier. Easier to screw up as well, but we have the comment. So the node of this adjacency that we just created will then be set to this adjacent node. And then we should probably up degree of node. And that should be it. That should be it. But we're going to want to do this both ways. So when this is going to kind of be the add impl, right? The implementation. Because when we actually add an adjacency, we are going to want to say that two are adjacent to each other. So we're basically going to say impl on A, B, and then BA. Okay. Does that make any sense? So when we add an adjacency, we add to the list and degree of both nodes that we are calling adjacent. I don't think that's too insane. Okay. So this could be thought of as like add edge or edge, adjacency list edge. Okay. That should be it for our adjacency lists. That should be all we need. Okay. Now we need build adjacency lists. So we are here. Interference graph pointer G. Well, it's not an interference graph. We called it an adjacency graph. Okay, Jesus. We have IR instruction list pointer. And then we have register allocation info. Coolness. Now this is just going to have to return nothing because it'll write to the adjacency graph. And then we're probably just going to have to move this thing down. To below the lists. I mean, either way, we're going to have to forward declare something. What is your issue, dude? Incomplete definition. What? I don't care. What do you want me to do about it? Let me just forward declare list? So messy. Okay, so this is gonna have to move up at least somewhere. Is that okay? You gonna freak out at me now? Unknown type name adjacency graph. Oh my god, I want to kill somebody. Okay. So our adjacency graph has to come before basically everything. And if it doesn't know what they are, I don't care. See, these are incomplete types. So we're either going to have pointers here. Oh, this is so annoying. Why? Why hath God forsaken me? Seriously. Okay, just go before you started moving everything around. Before you played with this for a little. Okay, and the problem is I can't create a list here. Create a list pointer. Do that. And shut up. Okay. We did it. I think that makes sense. I think that's fine. I mean, I guess technically it's going to be like an array. Yeah. So we'll say calloc, and then we want G matrix size of how many bytes? An adjacency list node. Yes, 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 yes. So we're going to have an array of adjacency list nodes. And this is going to be what? So assign corresponding indices to each node. Assign corresponding indices to each node. Well, okay. That means that we probably just have to do a for loop. With instructions. Okay. And then basically we can say list at get instruction index. See, it should be a node. So this list really just needs to be a node, right? Is that correct? Let me see. So yeah, I don't think we actually need a list of nodes. We need an array of nodes in our thing itself, graph. Okay. So now we have the proper, dot index. And then this can equal get instruction index. Okay. Then we can say the color is equal to the result in case there is any pre-coloring done. And then the instruction just refers to the instruction. That's the struct that we just created up there being populated. So for every instruction in the list, create and fill out the data for the adjacency list node. Then we basically just have to build the list, which we've done many times before. We're going to have instruction list pointer A. A equals A next. And then these are going to be B. And effectively, if A instruction is equal to B instruction, we can skip it. And then we can say, so we're going to use the adjacency matrix to build this. If adjacent in the matrix of A index and B index so if they are adjacent in the matrix, then we would like to add this would be, whoops. So the adjacency list node would be glist at A instruction index, right? And then I'm probably going to have to get the address of both of these. Okay. This sets the graph lists, or the graph list array, really, to the proper thing. Okay, what's in the notes? What's next? What's next? We're so close. Then we can build the coloring stack. We could print out the adjacency list array. That's probably a good idea. Let's try that. Okay, so we're not going to spend very long on this. And we're basically just going to take in an adjacency graph. Let's make it what we need. Array size t size. Okay. For size t I equals 0. I'll get there. I is less than size plus plus I. So for every node in the array, print out the instruction ID which is going to be so we're going to need a little instruction iterator or a node iterator. I guess we could just use array. Here, we'll do this. This node pointer it equals array. And then we'll say it is equal to array at I. And array at I? I guess we can just not have it be a pointer. So it dot instruction dot ID. Okay. Then we're going to say if it has a color, print that, please. Which is probably just going to be R, something like that. And then so then we actually have to print the adjacency list. So this is when we get the list. Okay. So this list here, print adjacency list, we're basically going to say if list, print a thing to handle the first one. And this is just going to be list node index. Why not? And then we can say list equals list next. This is just a bit of an unwrapped loop. For this, which we basically just say list equals list next like this. And then we'd like to print out things with a comma. And then at the end, we'll just stay consistent with printf, a new line. What? Oh. Keyboard, new keyboard. Okie doke, everybody. We can now print an adjacency list. So we should do so on it.adjacencies. And then at the end of this, another new line. And then we can try and print out the adjacency array after we create it. Print adjacency array of G list and G dot matrix dot size. Ruh-roh. Something went wrong. Very wrong. So I think we're just getting to here, but then it stops flushing. I don't think it's actually this. Okay. See, that works. So when we then call build adjacency lists, it breaks. So before build adjacency lists, let's call a flush on standard out. There we go. Wait, did that work? Why did that work? So everything's fine here. Everything's fine, but as soon as we go to print again, okay, it works again. I don't know what I changed, but it does work now. Lamau. So as you can see here, this is the adjacency array. And each one of these is the instruction ID. So this is like global address 0 and stuff. 1, 3, 4, 5. And you can see that these match these. But then we have some that are just 0, 0. So this makes me think that we should set IDs in a different place. Yeah, so after we recollect instructions is when we should set IDs, I think. And before we print the adjacency lists. That works. So where should we set the IDs? Let's try here. There we go. Now we have the proper numbers and everything. And as you can see, it works. The ones that have registers are properly, I mean, they're there, they're assigned, they're in the lists. And then, for example, 10 has a whole bunch of adjacencies, but some of them are duplicated, which I don't think is a good thing. So how are we getting duplicated adjacencies in adjacency lists? Oh, I already know what it is. So the problem is when we're going to add here, we actually are looping over all instructions A and B. So the fact that we add both to both isn't actually good. We want to do the impl. Is that actually... Okay, that stops all the duplicates. That's good. Okay, we now have all of our data that we should need. Crazy. So, what do we do now? We build a coloring stack. Right? So we're just going to do the same and G info instructions. I'm pretty sure that's what I need. Let me check my notes. Coloring stack. Yeah, that looks correct. That looks correct. So we use a copy. That's just what we use later on. What? Okay. So we're going to need a way to actually store a list of numbers. So we're just going to have a linked list of numbers. Surprise, surprise. So this is going to be register allocation info. I don't know what that sound is, but it's kind of terrifying, by the way. Hopefully it's just like the plumbing or something. And then adjacency graph. Gee. Gee whiz, Wally. Okie doke. And then we're going to need a number stack, or like a stack that holds numbers. I mean, let's just go as dumb as possible. It's really not a big deal. Very cool. Okay, number stack. There we go. So we're going to create a number stack. And then call it stack, calc 1 size of number stack. Then we can say, yep, it should be good. So now, the coloring stack actually needs a copy of that adjacency list node array. So this is going to be the adjacency list node array, which is going to be node. I could just call this array. That's probably the way to go. Which is going to equal, I guess we're gonna have to allocate first, which is G matrix size and size of adjacency list node. Then we can mem copy into array from glist, and this is going to be these two numbers multiplied. Okay. Is mem copy in string? I think it is. Okay. Is this gonna work? This isn't gonna work. We need to actually copy all the adjacency lists within each one back. Well, for I equals 0, I is less than G, matrix size, plus plus I, and we're basically going to have node pointer new node, which is literally just going to be pointer arithmetic array plus I. Then we're going to have node, which would be glist plus I. Right? Then we can say new node is equal to node, and not the pointers. I actually want them to copy the data. And then we need to copy adjacency lists. So we're going to say for adjacency lists adjacency. We'll just do adjacency iterator, which equals, yeah, new node, right? No, this will equal node adjacencies, because this is what we want to copy. Okay. Woo! Oh, boy, boy, boy. Okay, so for every adjacency, then we're going to want to what? Adjacency list, add impl. Is that right? Yeah, that's right. That's right. And the impl is going to be on the new array, new node. And then this is going to be the adjacent node, which is going to be whatever was adjacent. Okay, copied. Done. We now get into actual register allocation. Not even yet that yet, but we actually get into the Briggs algorithm, which is close. Register count. Matrix size. Okay. So the reason we need count is because we're basically going to do while count. And then at the end of this, well, this is going to be, yeah. Oh man, this is going to be rough. I think we're going to have a nested do while here. Okay. So basically, degree is less than k rule. This is what we're going to apply, which is a graph theory rule. The graph G is k colorable if for every node n in G, the degree of n is less than k. That's it. So char done equals 0. Do wow, done. And while there are instructions left, okay. I think this will make sense. This will make sense. Now we can say immediately stop this inner loop unless these very specific things happen. So what do my notes say? We basically have to go over the entire adjacency list. So for every node in the array, okay. So I equals 0, I is less than G matrix size plus plus I. Adjacency list node equals array plus I. Okay. I think that makes sense. And then we're going to say if it's already been colored or it's already been allocated, ignore that baby. Okay, then we can actually apply the rule. If node, Jesus Christ, that scared me. Node degree is less than k. Done equals 0, we're not done. We can make a new number on the stack. So push onto color allocation stack. This is basically going to be our number list, our number stack. Remember that? Honestly, it should equal null at the beginning, but I am going to steal this. Right? Okay, so now we're going to say number stack new number is equal to calc blah. And then we can say new number equals I. New number next equals stack equals new number. Okay. So then we can set our node as allocated. Okay. And then we've handled this node, so we can remove the count. Okay. Okay. And then what happens in this outer while loop? So if we get done, but there are still count left, right? So if count, basically, then what we need to do is determine node with minimal spill cost. Oh boy, it's gonna be a whole thing. So we're gonna have min cost, and then we're gonna have node to spill. Okay. So this will hold the index of the node that we should spill. So now we're going to loop over the entire instruction list. Okay. And in this whole instruction list, we're basically going to do a very similar thing to right here. So instead of I, what are we going to add to it? This is going to be it instruction index. Okay, so we should have our node now. And then we can set its spill cost to, if it has neighbors, then we can set it to the spill cost over the degree, just preventing a divide by 0 here. Otherwise, we can just do, I don't know, some invalid number. Okay, now, if node degree, so if it has neighbors, and if the spill cost is less than or equal to the minimum cost, right, then what we can do is update the minimum cost to the current node spill cost. And then we can say node to spill equals this thing here. And then, yeah. Oh, can't forget. Then it's been allocated. And we can say if not minimum cost, break. So if our spill cost has gotten down to 0, then just break here. Stop trying. Otherwise, what is this at the end of the 4? Okay, yep. So at the end of this 4, we should now have the node with minimum spill cost in node to spill and the minimum cost. So we can say, basically push it onto the stack is the Briggs algorithm, the Briggs part of the Chitin-Briggs. So just pretend that everything will be fine and everything should be fine. So we have node to spill as our new number. And then we have, what do we have? Should probably return the stack, by the way. Okay. So once we've pushed the number, do we need to set allocated? I think we've already set allocated here? Question mark? Yeah, so we need to remove count because we dealt with the node. I think we should set it to allocated still. I just feel like these things should happen together. So we're just gonna say array plus node to spill allocated is equal to 1. Yeah, so we just want to make sure that that is allocated, the node to spill, which it should be already, but maybe this is wrong, right? Maybe that shouldn't be there. Yeah, because we're not allocating anything here. Okay. Then let's make like a little print number stack thing and see what we get. Here, I'm just gonna do it by hand, print number stack. Yeah, we'll leave it in here for whoever's next. Stack equals stack. Next. Oops. And we're basically just going to printf percentage %zu. Okay, we're going to have to do the whole thing. Stack. And we're going to say stack equals stack next. And then if still stack, print thing. But this time like that. And then print a new line. Come on. Okay, something went wrong. Hey. Well, let's try and print that number stack, huh? Okay, what do we get? We sure got something. Print number stack if it's not 0. Can we do not 0? There's a lot of zeros here. Are there duplicates? 16, 36, 35, 34, 33, 28, 27, 26, 25, 24, 20, 19, 17, 15, 14, 13, 12, 11, 10, 9, 8, 7, 1. Or no duplicates. Other than the bunch of zeros, this looks correct. I would venture to say it is correct. So I mean, we're so close. All we have to do is color now using the coloring stack, right? That should be it. Color. Oh, Sarade says, I think Twitch is back. Pog. Legendary. Sarade says, never mind. Rip. Oh, feel so bad. So color. What is color gonna have to do? Let's look at my notes. Graph coloring. Okay, quite complicated. Thanks, sorry. He says, I'll try again later if you're still streaming then. I've probably got less than 40 minutes left. Okay, updated Sorade. Good. Okay, color says info stack. Okay, so we're gonna need like our register allocation info thing. That's what info stack probably refers to. Then we're gonna need, we're just gonna need all our instructions. We're gonna need our node array. And then node count. Something like this. That's rough. Okay. Yep, I'm a genius. Register allocation info. And we can just pass in info, stack, instructions, glist, whoops, glist. That should be fine. Oh. Okay, we are here. Okay. So the coloring, we're basically just going to be popping off of the number stack, is the idea. So let's go through our number stack. Right, number index, let's just call this I. While I equals I next. How about that? Okay. Then we should get the node that has to do with this thing, which is going to be array plus I number. So we have now popped this node off of this stack, and then we don't want to overwrite things. So if there has been anything written, or there is any coloring there already, just ignore it. You can now say register r equals 0. So this now brings us to actually choosing R, the register that this node will be stored in, aka this instruction. And to do this, we're going to need K again, which is going to be equal to our info register count. Then we're going to have char putter register interferences, I guess. This will be like a bunch of bytes that have to do with, you know. Oh, whoops. I didn't do that right. Each byte refers to register in register list that must not be assigned to this node. to this what? We'll go with that, to this. We'll fix it when we can, when we know more. Okay. Set Boolean values based on coloring of neighbors. Okay, so our register interferences, we're basically going to say for each one of our adjacencies, remember that. I called it adjacency iterator usually. And this is going to equal node adjacencies. While adjacency iterator equals adjacency iterator next. Yep, that's a lot of craziness, but that makes sense. Then we can say if adjacency iterator node and its color, right? So its result. So if it has been colored, then we need to set that color in register interferences so we don't pick it because it's a neighbor and it would interfere. Okay, so we need to say register interferences at this color are equal. Oh yeah, that felt good. To 1. And this is probably at -1. That way we convert the count to the index properly. Okie doke. So now, do we have to do anything else? That should be it. So now we can do, we can't do I, size t, x equals 0. X is less than k plus x. And then in here, we want to say if this register is actually not interfering, R is equal to x plus 1. Break. So it'll stop searching in this loop. And then we'll go to the next thing to color. Okay, but that doesn't actually work yet. So if we don't find one, then what, right? Even if we do find one. So if we do find one, basically we should say, if we don't find one, put in a big panic and say, basically cannot color graph in with blue colors, right? And then we can say have to do. Okay, so maybe let's do like, instead of a panic, we'll do it to do. Cannot color graph with CU colors until stack spilling is implemented. Remember that whole spill thing? Well, this is the case. Basically, if we can't actually assign a register, there's not one free, then what we're going to have to do is put it onto the stack and save it there as a value instead of saving it in a register. But we're not there yet. We are not there yet. But in any case, we can free register interferences once we're done using it. And then if R exists, we can basically just say we have node color, and it just is equal to R. Done, colored. Okay. Now, once we get out of this big loop, we're going to have the adjacency list copy have all the proper colors. Not even the copy, the actual adjacency list. However, that's not really what we need. So we're going to loop over everything once more. Equals 0. I is less than node count plus I. And basically, we're going to get the node, which is equal to array plus I. I mean, really, it's node array at I. We don't need a pointer right now. We can get the instruction that has to do with this node. We can get the color. Okay. And then all we have to do is say if instruction dot type is equal to ir_phi, do certain thing. I don't think we even need an else. Then we can say do not overwrite pre-allocated registers, in which case we can say if instruction result continue. Then we can say actually write to the instruction result. Just making sure that my notes don't say something different. There you go. Okay, then for ir_phi, we have to color the phi arguments. So what we're going to have to do is basically say for phi argument, because all the arguments should be stored in the same register, as you know. Phi equals instruction value phi argument. Phi equals phi next. Okay. So for every phi argument, we would like to say that the phi value result, is equal to R. And then we should probably also get the adjacency list node. Phi node, which is going to equal array plus phi value index. Right, and then we can say phi node in color equals R. Okay. Here's the trippy thing. We then have to say if this is a phi node, should we also follow it? Right? So like if phi value is a thing, do we have to follow it? To do. Should we follow phi value here? that's not clear. Should we follow argument recursively if it is also phi? Okay. Oh, Pog. That looks like registers allocated. Ay. Oh, yes. All of these numbers here are registers, right? I'm pretty sure. How did I do this? Yeah, so the result format is here. You can see I put a %. Let's put an R there instead of a %. Oh, yes. Look at that. So you can now see that all of these have registers assigned. Oh, that's so Pog. And it looks like it even works. This is stored in R1. Oh, it looks like it might even work. That's so Pog. Yes. So do even the phi's work? This is a function return, so it's R1. This is a copy from this phi, no? Yes, 44. So it's in R1. So 17 should also be in R1. Yes. That's a copy of 16, which is in R2, because then we have to use R1 and stuff. That looks wrong. This is definitely wrong. We can't store both of these in R1 if we're about to use them. Is that correct? What went wrong? R equals node color. Node color equals R. R equals x plus 1 minus 1. Well, if we think about it, it's at least close. Okay. So now, what do we have? So now here, when we say to do emit code based on intermediate representation and context, I mean, we should just call emit function to do generate function label. That's important. Emit instruction to do handle IR type, emit block. Okay. So now basically just for every function, right? Yeah. For IR function equals info context. I guess I don't need to go through info anymore. I'm in CodeGen. Oh god, my voice. CodeGen all functions, function equals function next. Emit function in this context. And just call it function. And then just do that. Now handle IR type 15. Okie doke. Does it actually work? I think it actually works. That's nice. Handle IR type. Okay, so case 15. What is 15? That's not really that helpful. IR global address. CodeGen global address. So we're going to feed it the context. This is horrible. Okay, what does this actually do? So we're going to steal this. Okay. So femit in the current context, a lee instruction, load effective address. We want to load a name, a symbol, rip addressed, the name is going to be instruction value name question mark. So to figure it out, we can go here, see what global address uses. Yep, just name. Target is a register, no? That's got to be a register. Oh yeah, so target referred to the register descriptor before. But now it's going to refer to where this instruction ends up in instruction result. Fuck. So it's doing that same thing again. So it now just doesn't work. Doesn't matter that we just added stuff, or if we remove what we just added, it just doesn't work. So let's see if we're returning from here. So we're not even getting through register allocation. That's not good. Why are we crashing in here? Everything was going fine. That just breaks entirely. Still breaks. What is breaking it, though? All of this not happening is fine. Is it something like phi to copy? No. Because we're obviously getting to the point of print adjacency matrix for the second time very clearly. It's right here. So if I were to flush here, standard out, you can see that we are making it there. What about here? Yep, made it. Okay. What about here? So as you can see, we are in build coloring stack and failing, because that flushes standard out and we see it update, but this doesn't. I can put it here. And you can see it still doesn't flush, which means that yes, it is this build coloring stack. So something in here is going horribly wrong. Sometimes. Any guess on what that could be? So when we build the coloring stack, stack is equal to null, right? We never just dereference stack, right? Nope, never dereference stack. So if it's null, it doesn't even matter. Node dispil equals it instruction index. So we should have set indices again here. Okay, just checking. So something within build coloring stack. Here, I'm gonna put it to do. Fix me. There is something in here crashing. Okay. we're gonna now commit all of this code because we just made a bajillion changes. And I have to go soon, so I'd like to get this code uploaded so if somebody wants to take a look at it and try and fix it, they're not just stuck waiting for me. Okay. Fair enough. Type def struct to use. There we go. I mean, that's everything I did today. Hunky-dory, hunky-dory. Let's just push simple math as an example as well. And that should be good for now. I'm gonna commit the commit. And then bougie. And we can basically just say codegen. Like 99.9% of register allocation. Woot woot. We can now allocate registers. All that needs to happen from here is to actually handle the different IR instructions in the backend, which isn't too difficult. We are so close to getting the compiler working again. Woot woot. Okay, now we're just gonna booshy. And then I am done, dog. I've been going for like 6.5 hours. And I am killing for some food. And some water, to be honest. Instead of hello and welcome, it is now goodbye. First time chat, Flying Octopus 22 says GG. Blessed, Flying Octopus, bless. But it works. Feast your eyes upon it. It doesn't always work, I know, there's something crashing here. I don't know what it is though, so not much I can do about it right now. It's probably something really trivial that I may fix after the stream if I realize it, but otherwise we'll be back here and fixing it next time. Thank you so much everybody for watching. Be sure to check out my links down below. The GitHub will have the code we just worked on today. Something like here. One compiler. As you can see, we now have like 99% of register allocation done. How about that? So what we can do is, or what you can do, I should say, is come check out this repository and figure out, come tell me why this crashes in build coloring stack. Why does it crash? But if not, don't feel bad. All we're going to be doing is working on this next time. So feel free to follow, hit that button. If you want to see VODs of any of my previous broadcasts or this broadcast, check out the YouTube link down below. I would really appreciate any and all donations that do come in. If you leave a message, I'll read it as long as it's appropriate. And if you leave your name, I'll attribute it to you. So I really recommend doing that. If you can't give money or don't want to, I do not mind. All I care is that you show up and have a fun old time. So if you're showing up and having a fun old time, then don't worry about it. You are good. That's exactly what I want. Thank you everybody so much for watching. This has been compiler dev today instead of OS dev, but you know, we keep it low level, we keep doing it, we keep going. Thanks all so much for watching. I'll hit your ears next time, baby. Bye.